we approached Simon Larder, and Simon agreed to put the training together for us. Simon is the chair of the CSA standard B72, which for us is the equivalent of the code book. So he's obviously the subject matter expert that we needed to do this training, and we were able to come to an agreement with Simon to provide this training. Now, just a few things about this. So for those of you that are safety codes officers in Alberta, this does count for professional development hours. So the total is going to be approximately 4 hours. We don't know exactly to the minute because this is the first time we've done it, but I would suggest it's probably going to be somewhere in the 3.5 to 4 hour range. Now, each of you should have received a quiz sent out to you probably yesterday from Dan Green. So the quiz is not mandatory for you to send in. However, if you want a certificate of completion for the course, you must complete the quiz. You must send it to me, Larry, and my email address is on the quiz. You must send it to me by Tuesday, October the 4th. If I get it after that, I will not consider it. You also must get a mark of 15 out of 20 correct or more on the quiz in order to get the certificate. So for those of you that want a certificate of completion, you have to submit the quiz. You have to get a mark of 75% on the quiz. I don't know how much more clear I can make that. Your professional development hours will still count. You, of course, have to submit those yourself. You do not have to submit the quiz to get credit for the professional development hours. What you have to submit the quiz to do is to get a certificate of completion that you passed the course. I don't know how much more clear I can make that. If that's not clear to you, please put a comment in the chat box and send it to me. I see a couple of people are commenting that they did not receive the quiz. If you did not receive the quiz, please respond to the email that sent you the Zoom link, and Dan or Lori will send you the quiz. Okay. So all of the quiz questions will be answered in the presentation by Simon. Just a couple of other quick announcements. The Electrical Inspectors of Alberta Annual Technical Conference is coming up February 10th and 11th. As always, it will be held at the Chateau Louis in Edmonton. It is also available, as it was last year, via Zoom as well. We haven't finalized the presenters for the technical sessions on Saturday yet. Once that is done, we will be sending out the registration forms. On that note, I would get you to welcome Simon Larder.
Harry, you muted yourself.
Sorry about that. I did not mute myself. Somebody muted me. So Simon is involved in the installation, inspection, maintenance, and design, the whole ball of wax when it comes to lightning protection systems. He is, I would suggest to you, maybe Canada's foremost expert on lightning protection systems, certainly Alberta's. And on that note, I would turn it over to Simon. Simon, it's all yours. The one thing I would ask Simon to make sure he does is identify whether you want to take questions on the fly or whether or not you want the questions held till the end. On that note, welcome, Simon. Thank you for being with us today and as well as tomorrow.
Thank you, Larry. I appreciate the introduction. Don't know if I'm Canada's foremost lightning expert, because I know there's plenty of people in the country that know more about me than lightning protection, but my sort of unique synthesis of code writing and industry knowledge from being in the business for 25 years may be unique to Canada, so I'll take that. I don't mind taking questions on the fly. However, I'll just admit right at the beginning that this is my first time doing a Zoom presentation for so many people. So I may or may not be able to, to even accommodate questions on the fly. But you know what? If you've got a burning question about something I've said, pop up however you're supposed to do it in Zoom. I don't know how to do it, but if I notice it, great. And I will attempt to answer it on the fly. Otherwise, I will leave time at the end for questions. And as for why this is suddenly in the electrical inspector's purview, I would apologize, but it may have something to do with conversations I've had with the safety codes people from the province about the fact that lightning protection has historically been completely unregulated. So just about anybody could hack together a lightning protection system, which to me, as a professional in the field, is dangerous. You have homeowners all the time who try and do their own electrical installations, and that sometimes works out, but sometimes doesn't. Creates a hazard in the home. Same thing when somebody unqualified in lightning protection goes ahead and tries to put a system together. Maybe they connect it up to the gas line improperly or something, and now all of a sudden you've created a hazard. So I did have conversations about that kind of thing with the chief inspectors of the province. And oh, there we go. You're welcome, Clark. But anyway, yes, so it's probably something to do with those conversations that I had. There's a hand up. Is that somebody asking a question? By all means, Jerry, go ahead before I get into the presentation.
Yeah, they give you a brief history of how this happened, right? I'm chair of the electrical subcouncil for safety codes, and I'm also liaison on the building subcouncil as well. So I actually, one of our meetings with building subcouncil, it was brought up that the inspectors of building inspectors have no idea what they're looking at. They don't know what to do, and they don't even want to do it anymore. And this happened about a year ago, I guess, a little better than a year ago. We started talking about it, and then we had a joint meeting between the electrical subcouncil, which was mostly myself, and building subcouncil, and they suggested that it move over to the electrical subcouncil. Would be better. It's a better fit with the electrical subcouncil than with the building. So we actually set to work. We put the motion forward, and we set up the mutual stand data to move it over to electrical. So that happened in May, I believe it was, when that started. So
oh, great.
So
Yes,
that's how it came to be.
Okay, yeah, I knew that there had been some initial action, and it did go all the way through the safety codes councils, the electrical and the building. So there were lots of official channels that this went through. It didn't happen by accident. But with that said, I will, I guess, go ahead and start the screen sharing, and we can get into the presentation itself. So, as Larry indicated, I'm Simon Larter. I am with Dobbin Lightning Protection down here in Calgary. And this is a presentation that I've modified from some others I've done for other groups, but to give you electrical inspectors and associated trades an idea of what it takes to inspect a lightning protection system. That's just a wee bit about the company here. Doesn't really matter so much to you because you're not buying our services. But the thing to take away from this one is that we are affiliated with just about every major industry group in lightning protection in North America. Canada doesn't have a homegrown lightning protection industry group, so we are associated with the Lightning Protection Institute in the States, Lightning Safety Alliance. We are also part of CSA Group. Well, we work with CSA Group. I'm the chair of the technical committee on lightning protection and was largely responsible for the rewrite of the Canadian Lightning Protection Code that happened a couple of years back. So that's why we have a 2020 edition instead of still a 1987 edition. But yes, in any case, that's us. That's the company I work for. And let's move along. The Lightning Safety Alliance was the initial generator of some of the content of this presentation. I am using some of it with permission, and those parts I'm using with permission are copyright. I won't call out necessarily what parts those are because that doesn't matter to you, but just that I'm doing my due diligence here in the legal sense by saying part of this presentation was generated and owned by somebody else. What are we going to talk about here, ladies and gents? Well, first of all, we're going to give you an idea of the importance of lightning protection and a general understanding of what it's all about. We want to make you aware of the 5 essential elements that go into a lightning protection system. Every lightning protection system should have these 5 bits unless it's a special case, and I'll tell you exactly what those are. How do the building and electrical codes interact with lightning protection? I'll go through that specifically and in some detail because that definitely applies to you. And then we will show you what you should and should not be looking for in a lightning protection system, or what you should and should not do, which you may run across should you be asked to inspect such a system. How are we going to get to those learning objectives? First of all, I'll give you an idea about the lightning phenomenon. Now, this is my favorite portion because I just think it's cool. Lightning's an awesome, awesome phenomenon, and the science of it is just as fascinating. So we'll go through that just so you have an idea of what the stakes are. What are we dealing with as a phenomenon? Then we will look at those 5 elements of the lightning protection system. You, as an inspector, probably will come out and mostly what you would be looking at is the roof level stuff, but we'll talk about everything, soup to nuts, top to bottom, so you'll know what goes into an LP system. We'll talk about the codes and the regulations that apply, of course, as you're all familiar with the electrical code, but I'll give you a wee bit more detail about the lightning protection side of things. That's CSA B72. And then for you, of course, inspecting the lightning protection system, that's definitely something that you are going to need to know a good bit about. And I've got a checklist that I sent over to EIAA that I've developed for use in the field that may be of use to you. I don't know if it went out in any of the emails, but it certainly is available if anyone's interested. There is a checklist, you can modify it for your own use. And I sent that along. It doesn't cover every possible situation, but it covers the majority of situations you will see. And then I am going to show you a bunch of photographs of good installations and bad installations, and you will immediately be able to tell the difference. So with that said, oh, and by the way, I will pull in a 15-minute break because you all can get up and walk away from your screen. I, on the other hand, cannot. And because I'm drinking coffee and I'm going to have to hydrate because I'm talking a lot, I'm going to need a 15-minute break at some point in the middle of this conversation. So fair warning, I'm going to give you time to get up, refill your coffee and get a drink. But so what the hell are we talking about when we're talking about lightning? We want to understand the phenomenon before we want to understand how we're going to protect against it. And I don't know if any of you, other than say Larry and maybe Dan were at my presentation at the Electrical Contractors Association. Apologies if any of this is stuff you've seen before, but we'll go through it and you'll have an idea now of what lightning is. This is one of the easiest ways to conceptualize it, honestly. It's a static spark on a huge, huge scale. Just like you shuffle across the carpet and then shock yourself when you touch the doorknob because it's kind of grounded. The same thing happens on a massive scale. So you're generating, when you walk across a carpet, static electricity. The rubber soles of your shoes are rubbing against the carpet. It's causing free electrons to start developing, and a charge builds up on your body. When you reach out and touch a grounded system, that charge wants to equalize out to ground again. So you get that wee spark and it hurts the end of your finger. Sucks. Static electricity is essentially the mechanism that develops in clouds. So in a massive thunderhead, those are huge convection cells, right? So you've got rising air, you've got falling air, and with that rising and falling air, you've got tiny ice particles called graupel, you've got dust grains, you've got water molecules. These are all rising and falling, sometimes bumping into one another. As those interactions happen between the particles and the clouds in the convection cells, you do get electric charge starting to build up, free electrons starting to build up. Those, for reasons that aren't seriously well understood, start developing into charge centers in the cloud. They tend to cluster. So you'll have a main negative charge in the cloud and a main positive charge. And then when those start developing, what happens is those become powerful enough, that electric field becomes powerful enough that it starts affecting the electric field in the ground. So that's, you can see in the bottom of the cloud there, you've got that small positive center right where the rain is on the left. Then that starts to push away the positive charges in the ground and attract negative charges in the ground underneath the cloud, opposite that charge center. What happens at that point is the voltage starts building up to the point where the air is going to start ionizing. And you get what's called a stepped leader. It's a stepped leader because it jumps down in steps. That's why lightning has that characteristic jagged path. It jumps down. It's just finding a way to get down through the air, whatever way it possibly can, in a completely kind of random way. It's going to arc here and there and jagged. And that's just an ion channel. That's not the main lightning spark. When that ion channel gets close enough to ground, you start getting what's called a counter leader coming up from the ground. It develops from the tops of trees, the tops of buildings, whatever. And that's a complementary ion channel that starts moving upward towards that downward stepped leader. Once those two ion channels meet, usually something along the order of 45 meters above ground, 30 to 45 meters. Once those two channels meet, now that you've got a circuit, you've got an electrically conductive path for the main lightning charge to flow. And it does. It's going to pull those charges out of those various centers in the cloud, send them rocketing down to Earth. That's the lightning strike that you see. So that's the overview of the lightning phenomenon, but there's various types of lightning. The one that we are interested in is cloud to ground, because that's what we have to protect against. That's the main mechanism that we want to capture in our lightning protection system. But in any given thunderstorm, there's going to be other lightning phenomena. There's going to be intercloud. There's going to be intra-cloud. There's going to be cloud to air. They call those sprites. Airline pilots see these occasionally. They're rarely caught on film, but they're starting to be more and more. Those are slightly less understood. We don't really know why it's going up like that. But it used to be when the CSA was, not the CSA, Environment Canada was tracking lightning. It used to be tracked and statistically measured by the amount of thunder days. Any day that thunder was heard in a given location, they counted that as lightning. But that could have been any of those types of lightning, intra, inter, cloud to air. Didn't even have to be a cloud to ground lightning strike. In the most recent data set that Environment Canada put out, they did accommodate for that. So now they only count cloud to ground lightning, because it was only about 15, maybe 20 years ago that we got a full Canada-wide network of lightning detectors all built out. So now they're refining their data set. And it used to be from their data set, Calgary had something like 0.8 strikes per square kilometer per year. Now, when they refine the data set for just cloud to ground, we're down to about 0.65, something like that, strikes to ground per square kilometer per year. This, just to give you an idea, is a very high speed capture of a lightning strike developing. Bang. So what you would have seen there, and this is going to continue on, by the way, what you would have seen there, of course, is that stepped leader coming down. It's trying different channels. It's branching through different channels there. But as it's coming down towards ground, and this is something like 15,000 frames per second. I can't actually see the top of that screen, but you can see the lightning is continuing to follow that channel. There is a channel developed. What was happening there is it was pulling in charge from all different areas in this thundercloud, not just the one initial stroke. That initial stroke, you've got a lightning strike, which happens when you have a connection of that ion channel and the electricity starts to flow. But each strike can have multiple strokes. In fact, most strikes have multiple strokes. The ion channel's there. It's going to have pulses of electricity coming down from cloud to ground, sometimes from ground to cloud, but mostly from cloud to ground. And it's going to be pulling in from charge centers in various regions of the cloud. It's going to break down over the course of something like 60 to 150 microseconds, but there could be multiple flashes within that one lightning strike. That's just a good thing to know, because that kind of determines how much current can flow through that ion channel once it's connected. We can look at a different step leader developing. Now, this is a lower energy one. It's taken a slightly tortuous path to ground. It's going to get there eventually. There we go. Eventually it got there. That's a lower energy lightning strike. It took a much more circuitous route to get to ground. It did eventually. But again, we had the same thing happening. That was a stepped leader. It's not always a direct path. It follows whatever route it can take through the air. And then it eventually connects up to ground. And down at the bottom, if you look at the very bottom of that lightning flash, you're going to see a short, straight bit coming up. And that's the final intersection where the counter leader starts coming up from ground, hits that downcoming ion channel, those meet, and then the current can flow. This, to give you an idea of the scale of lightning, is a very well-studied single lightning event that happened in the Washington, D.C. area in 2014. So what you're looking at in that inset there, that's the Washington Monument. You can see the Washington Monument is, of course, dwarfed by the lightning strike coming down from the cloud there. But they have a network of sensors, the National Oceanic and Atmospheric Administration, that detected this entire lightning strike from inception, where it pulled every piece of charge from out of that cloud. And this is a model of it. So the distance from the point of origin at A to where it eventually struck at B, almost 15 kilometers, going on 10 miles here. And that's just from A to B. You can see that there are other charge centers that lightning strike is pulling in from for its eventual current flow to the ground. And they're going all over the place. Just the main channel, what they chose to call the main channel, was 15 kilometers long. This will come back again in the future, later on in the presentation when I'm talking about what doesn't count as lightning protection. But just look at that lightning bolt, the size of that thing, very well mapped. It's a huge phenomenon. It takes place over a very long distance. So when we say that we're putting lightning protection on a building, we are not preventing lightning from striking. We are not attracting lightning in any significant sense. The only thing we're doing is giving lightning a path to ground should it come to that building to begin with. Because it's such a huge phenomenon and it can take place over such a huge distance, there's no way a single 300 millimeter tall lightning rod on top of a house is going to make any damn bit of difference to its likelihood of being struck. So this is just to give you an idea of the scale of a lightning protection system, or a scale of a lightning bolt. And that's pulling from all different charge centers in the cloud. This is just an animation of that lightning strike to give you an idea of what happened. And there was a very nice, very diligent grad student who plotted this well before we had any decent 3D modeling software. But he put together this animation of that lightning strike. So that is a huge scale lightning bolt. And that's all the different portions. And I'm sure it was more complicated than that too, but that just gives you an idea of the complexity and the scale of a lightning strike. These are just some random facts and figures. If you look at that 27,000 degrees Celsius, for reference, that's about 5 times the temperature of the surface of the sun. So at the center of a lightning bolt, that's essentially a plasma channel. It's broken down the air into constituent parts, and then it creates a plasma as it goes through there at that temperature, ridiculously hot. 144,000 kilometers per second. That's not stepped leader speed. That's the actual lightning bolt. That's the current flow once the stepped leader has combined with the counter leader. And then, of course, we have the whole lightning safety thing where thunder travels 0.2 of a mile per second, and 5 seconds means the bang's a mile away. But that's just one of those lightning safety things you tell kids. But we're on the metric system here in Canada, so I usually say 3 seconds between flash and bang means that it's a kilometer away, and get your ass inside. Mainly what I say about that. So, as far as numbers, lightning strikes the US 20 million times each year, which is quite a significant amount. That's Vaisala. They run the lightning detection network in Canada too. I'll show you that slide next. But the thing to take away from this one is that you have clusters of lightning density. Florida, of course, it gets a ton. The Gulf Coast, you're looking at Florida and Mississippi and Louisiana. Those get a lot right there down by the Gulf Coast. And then, of course, you have other clusters. You've got some in the Midwest there and the Central Plains. And then it tails off as you go over towards California. Gets very little. Oh, let's go back to that. California gets very little. Oregon, Washington, Eastern, the Western side doesn't get much. But I'm going to give you a little statistic later on that shows you that even though they don't get much, statistically speaking, it can still be really damaging. So BC doesn't get a whole lot. Vancouver gets very little, but sometimes they do get lightning storms and it does cause significant damage. So we do want to be aware that despite it being statistically rare, it will cause damage when it strikes. Canada, we don't have quite as nice a graph. They haven't generated one that's as nice for Canada, but you can see there's Eastern and Western Canada. The Environment Canada breaks it up for us there. You can see the red is, of course, all along the border. You get fewer thunderstorms and fewer lightning strikes because of less variable climate as you get farther north. But you still do get lightning strikes in Northwest Territories and Nunavut and places like that. Rare, but it happens. Good to be aware of. Lots of our lightning is clustered along the southern border. But the important thing for us is if you look over on the left-hand side there, you see that nice little northwestward line that's going up there, that yellow. That's the Calgary-Edmonton corridor. That is the Alberta Rocky Mountain foothills. That's where we live, and that's why lightning protection is my primary industry right here. So it's good to be aware that we are in one of the lightning hotspots in Canada. What happens when lightning strikes? Well, 3 to 5% of commercial insurance claims are lightning related. Depends on the year. That we anticipate that's going to rise as the effects of climate change become more pronounced. If climate zones move north, lightning activity moves with it. So if that border where most of the lightning strikes happen in Canada, if the climate moves farther north than that, well, then the lightning hotspots are going to move farther north too. We're going to get more of it, and it's going to be more destructive, the same way these storms have been more destructive over the past several years. Annual property losses exceeding $1 billion in the US. Still don't have that kind of information for Canada. Oh, but given we've got, I don't know, 10% of the population or so, and I would say it probably exceeds $100 million in Canada alone. That's just a guess. Don't hold me to that. I could ask an insurance person, but that's tough to track down. It's the leading cause of all church fires. I always thought that was ironic, but when you think about it, the architectural design of churches, putting up a steeple so we get closer to the heavens and closer to God, well, you're also getting closer to the clouds and closer to lightning. So I guess it makes sense that lightning is a leading cause of church fires. One of the leading causes of weather-related deaths, which is why I always, and I post this on LinkedIn weekly, I think, when thunder roars, go indoors. If you hear thunder, go inside, don't mess with it, because you never know. I've met people, I've met a guy who was struck by lightning. He survived, but you don't want that. You can survive a lightning strike, but it changed his personality. He lost his job. He couldn't get along with anybody. And that's if you survive. You might not. So just go inside, play it safe, don't mess around with lightning. And if you're going out into the wilderness, hiking, fishing, kayaking, check the forecast. If thunderstorms are forecast, you might want to think about playing it safe. Why do I take this so seriously? I had a friend of mine, a little kid that I saw grew up. He was 5 years old on the beach in North Carolina, struck by lightning while they were running for their car, and he died. And this is a kid I used to carry around as a toddler. So I take lightning safety seriously, and I'm telling you to take it seriously too. That's why. The average insurance claim is over $10,000. This has been rising year on year. Every year, insurance claims go up for lightning. We're packing more and more electronics into our buildings. We're putting smaller wires in, and especially the small telecom wires, garage door openers, security systems, fire alarms, all of the above. Those small wires and those circuits connected to those wires are easily fried out by lightning. And even a nearby lightning strike can cause enough current to flow or be induced on those wires to fry a capacitor and ruin a circuit board. So that's why the claim has been going up every single year. And you saw California does not get a whole lot of lightning. But in 2020, the average lightning insurance claim in California was $217,000, mainly because lightning caused a whole lot of wildfires. So there were a whole ton of claims, a whole lot of homes were burnt. And that's an outlier. That's the highest it's ever been for an average claim in any state ever. But just to give you an idea of the magnitude of the damage lightning can do. And there's some images of the damage that lightning can do. What you should be taking away from this photograph, in the bottom right specifically, is the roof is on fire. Lightning strikes, not always, but generally the highest point, or a high point, not always the highest, but it strikes at the top. The fire starts at the top and it starts burning its way down. If that house had sprinklers in the attic, they wouldn't even kick in until the flames were down below the point where the sprinklers could actually do any do any good for it. So the roof is almost fully engaged by the time the sprinklers kick on. Not a whole lot you can do at that point. That house is going to be a total loss. Not sure what the building on the left is. It looks like a warehouse of some kind, but same deal. Would have been struck at the roof, started burning at the roof, and burns its way down. Sprinklers don't do a whole lot of good there. And anyway, once that 27,000 degrees Celsius impacts a building, it's going to cause a fire. It usually rains during thunderstorms. That doesn't stop these fires from happening at all. Look, it's raining in that bottom right there too. The fire is going just fine. The rain doesn't do a damn bit of difference. That's the next day on that house. That house is a complete loss. I don't know if anyone on the call here has ever assisted somebody that was trying to clear out their house after a fire, but I have. And it's not just the fire that does the damage. It's not just the smoke that does the damage. Once the fire department gets out there and starts spraying water in, everything's got water on it. Now you've got smoky water on everything you own, your fabric, your carpets, your couches, your clothes. You're not coming back from that. That house is a total loss. It's going to have to be torn down and rebuilt. And that's, yeah, sure, insurance covers that, but insurance doesn't bring back your keepsakes, your mementos, your memories. Lightning protection could have prevented that. So, it's not just the fire. The fire department does a whole lot of damage too while they're putting it out. So those are always good things to know. And I think just put the lightning protection on and protect the whole house against that kind of damage in the first place. Of course, I think that. My business is lightning protection, but this is just to give you an idea of what happens. What happens when lightning hits stone? If it's a stone or a reinforced concrete structure, is it okay? Nope, no, it is not. Concrete is an admixture of Portland cement, lime, aggregate. And once that's all mixed together with water, that's a chemical reaction that creates the concrete. In that chemical reaction, you will still have water entrained in the concrete. That water, in the event of a lightning strike, the strike's going to go through 27,000 degrees Celsius, is going to flash fry that water. The moisture is going to expand as superheated steam, and it's going to blow chunks of concrete out. I've seen this happen on high rises, and chunks of concrete fall all the way down a couple of 100 meters to the ground below. I've seen this happen on chimneys like that. Even roof tiles right there, terracotta tiles. They don't have a whole lot of water in them, but lightning will still do damage to that. So that's the kind of damage lightning does when it hits concrete. Reinforced concrete, lightning will flash through it to get to the reinforcement bars. If they're discontinuous, you could have flashovers within the concrete that start to compromise the structural rigidity of that concrete column. So either way, it's probably better just to have a lightning protection system so you're not letting incidental parts of your building carry the current to ground. We don't want that. And just for funsies, here's what happens when lightning strikes a tree. You don't want to be standing next to a tree in a thunderstorm. That's only one of the reasons. The other reason, lightning safety wise, is that that current is going to ground out through the ground at your feet. And the difference in voltage between your left foot and your right foot as that current is dissipating away from the tree is probably going to be enough to cause extra voltage, will cause current to run through your body. And that can be enough to kill you. 3 people were killed in Washington, D.C. this year from sheltering under a tree during a thunderstorm. Do not shelter under a tree. It's a terrible idea, let alone getting shredded by flying bark and sticks if lightning strikes and it explodes like that. And incidentally, the mechanism for that, same mechanism as concrete exploding. The lightning current flash fries the sap expands as superheated steam and sends chunks of wood everywhere. I've picked up pieces of wood a good 30 meters away from a tree that got struck by lightning. So fairly powerful phenomenon. And again, you don't want to mess with it. Don't go under a tree, go indoors, preferably inside a building with lightning protection. But I can't control that part. Just get inside and stay safe. So now you know what we are protecting against. Give me a sec here. So we are protecting against the lightning phenomenon. How do we do that? So we're going to go through and talk about the elements of the lightning protection system. And these are the things that you will encounter when you go out and do an inspection in the field. So as I said, we don't prevent lightning from happening. We don't attract it in any significant sense. We try and work with, not against it. All we are doing is providing a passive system that provides a safe, highly conductive path to conduct lightning around or through a structure sometimes, around a structure safely to ground. So here, this is the mechanism I was talking about. You've got the charge center in the cloud up top. That's the negative charge up there. You've got a positive charge center in the ground. You're going to start sending positive ions up and over any surface, any structure, and it'll start sending up these counter leaders. It ionizes the air. The counter leader moves up, meets up with the downward stepped leader. There's your ion channel. There's your circuit. Lightning current can flow. You don't have to have a lightning protection system on your house for this to work. I'm just saying house because that's a residential structure we're showing you here, but this happens on any kind of building. The charges, the electric field runs on the exterior surfaces, and where those surfaces come together, say at a corner or an edge, that intensifies the electrical field because you'll have two fields coming together. That's the working theory as to why these charges start developing counter leaders that move up from a structure to then capture lightning. Now that's why we put our lightning protection in certain areas, and I'll go through that shortly. Here's the elements of a lightning protection system. You've got, starting from the top, air terminals, lightning rods, strike termination devices. They are called multiple things, air termination rods. There's lots of terms for them. You can call them lightning rods. It's one of the easiest things, but we generally call them air terminals as a industry term of art. That's the top. That's what captures the lightning strike initially. They assist in developing those counter leaders. I'll tell you why in a second, but that's why we put those up top. They're the things that initially take the lightning strike. And of course, we have to have a conductor to bring it safely, bring that charge safely to ground. You can see those there. We have bonding connections, and we'll go through what those are all for. Grounding terminations, you are already familiar with, of course, from electrical grounding, for surges and fault current, things like that. You've seen it a million times, I'm quite sure. And then surge protective devices are the last component of the lightning protection system. So those are the 5 elements of a lightning protection system: air terminals, conductors, bonding connections, grounding terminations, and surge protective devices. Those are the 5 things you want to see in any given system that is supposed to protect against lightning. Here's a typical commercial lightning protection system. It's courtesy of East Coast Lightning Equipment, one of the manufacturers we work with. But you can see, of course, those 5 elements. You have got upper left, you've got adhesive bases. Those are good for gluing down to a membrane roof surface or the top of a parapet coping, something like that. You've got the conductor running between, you've got the conductor fasteners, you've got the bonding connectors. In this particular instance, the structural steel framework of the building is being used as a down conductor. You are allowed to do that. If the steel is 4.8 millimeters thick or greater, you can use it as a lightning conductor. So that in this particular instance, in this example diagram, we're using the steel as a down conductor. You can see on the right-hand side there's a through roof connection, bonding connection to the steel. Then directly below that, you can see that there's a bonding connection to steel at grade and a ground rod. Over on the left-hand side, of course, you've got bonding connections it's showing roughly the water line or the electrical ground, surge arrestor on the main distribution panel. That's kind of an overview of what a typical lightning protection system will look like. And the other thing to notice, we haven't talked about anything yet about where to put lightning rods, but you'll see there's a lot of them. It is not just a single lightning rod on the highest point, say that atrium clerestory arch thingy. That's not the only place you put them. You have to put lightning rods on a whole bunch of other stuff on a roof too. So it's a bit more of a complicated system than people tend to think. I get calls all the time, people wanting to say, I'd like a lightning rod for my house. Yeah, I guess I could sell you one, but you're going to need quite a bit more than that if you want to maintain a code compliant system. So that's an immediate takeaway from that. Here's your residential system. No, I can't, sir, sell you a lightning rod from your house because it is more than likely going to take a lot. So even on this, it's, I guess that's a mid-sized family home. You've still got a number of lightning rods across the ridges, on the garage, on the dormers, on the chimney. It's the same 5 elements, however. You have lightning rods, you've got interconnecting conductor, you've got bonding connections, you've got grounding, and you've got surge protection. Those are the 5 elements in any system: commercial, residential, industrial, military, whatever you want. Any kind of structure is always going to have those 5 elements. Air terminals. There we go. Those are the actual lightning rods. They come in various models. The ones on the left, that left-hand one, it's an aluminum rod. We use copper and aluminum in different situations. Copper will, if moisture is introduced, copper will cause corrosion on exterior galvanized steel surfaces. It will make it rust a whole lot faster. Same if it's just painted steel, metal parapet copings, that happens quickly. The rust will, I've seen a galvanized steel roof rust through in about 10 years, and that's through. You can see into the building underneath it. That's because somebody put lightning protection on the roof. It wasn't aluminum, it was copper. The copper caused corrosion, and the roof wasn't very high quality to begin with, but it did rust through in a matter of about a decade. So we want to make sure we are using the correct materials. But if you look at the air terminal on the left, it's a pointy one. We used to use only pointy ones. Old lightning protection systems will have only pointy ones. However, right when I was getting into starting my career back in the 90s, the early 90s, there was some modeling done that showed that those blunt ones, not only safer, they don't hurt as much if you fall on them, but they actually produce a counter leader slightly more efficiently than the pointed ones. So those are ever so slightly better, a lot safer, and they work slightly better. So that's what we've gone to as an industry. You won't see very many pointy lightning rods unless somebody wants them for aesthetic reasons. We generally use nothing but the blunt ones now. The one second from the right is a safety tip. You can put safety tips on them just for a wee bit of extra safety in case somebody bangs into them or falls over on them. Believe me, I have been poked with a sharp lightning rod. It's not much fun. That's an occupational health and safety thing, I'm sure, but yes, that did happen to me when I was installing, and I didn't enjoy the experience. And you can see on the far right, that's a spring-mounted lightning rod. We use those a lot on high rises. It's got a safety leash that connects to the base. That's just so if the window washer's swing stage, for example, hits that lightning rod, it just bends over and flips back up when it's done. They're not perfect. They will break eventually, but they're better than having the swing stage knock a lightning rod off the top of, say, Bow Tower and have it fall 300 meters to the ground, or however many meters that tower is. How do we figure out where to put the lightning rods? Well, here's the operating principle that we work with. It's called the rolling sphere method. When I was mentioning that stepped leader coming down towards ground, and then there's a counter leader that comes up, reaches the stepped leader roughly 30 to 45 meters above ground, and that's the final point where the circuit completes and the current can flow. That 30 to 45 meters, that jump, that counter leader that comes up, that's the final breakdown of lightning. That's where the final breakdown of a lightning strike occurs. So what happened back in, I think the late 70s, early 80s, they started doing some modeling on this, and they were wondering why they would have an overhead ground wire above transmission lines. And they thought, okay, 45-degree angle down from that wire, that's going to protect our transmission lines. That's our overhead ground wire. Lightning's going to strike that instead. Turns out they were not getting that 45-degree angle worth of shielding, depending on the height of the wire. So they did some modeling, they did some statistical analysis and found that lightning was striking inside that 45-degree angle. So we no longer use an angle method to figure out where lightning might possibly strike. What we do is we take that striking distance, that last jump, the final breakdown of lightning, 45 meters, typically 45 meters. If we're going to use a slightly higher standard of safety for explosives and flammables, we will use 30, but 45 meters. if you posit a hypothetical sphere with a 45-meter radius, roll it up and over a structure, whatever that sphere touches, we want to make sure there's lightning protection. So let's give you an idea of what that looks like. Here's the 45-meter, okay, 150 feet. Yes, you can tell that came out of the States, right? 45-meter radius, rolls up and over the house. That roof is unprotected because that's where the sphere hit. Now we're going to put air terminals, strike termination devices, lightning rods, whatever you call it. We're going to add a full lightning protection system to that house, putting the grounding system in. And then once you've got, and surge protection, let's not forget that. But now that you've got lightning protection, bing, bing, bonk. Now you can call that house protected because we put the lightning rods on it. And when you roll that rolling sphere up and over, this hypothetical rolling sphere, it's not going to touch the house itself. It's not going to touch the roof shingles. It's not going to set the roof on fire. Now you're protected. So that's how we conceptualize the zone of protection that you get from any given lightning rod, is using that rolling sphere method. If we want to do it on a more complicated building, then we can. We're going to do the same thing here. There's that 150-foot, 45-meter radius rolling sphere up and over the building. You'll get contact at the outer edges there, edges and corners. This thing is just hitting all over. So you roll that sphere up and over the building, and everywhere it touches is a potential attachment point for lightning. So I'll just let that animation go, have another sip of coffee. You can see those are all the places that the rolling sphere touched. So we're going to want to protect those places. So why don't we put lightning protection on? Let's get those lightning rods in place. Let's get those conductors. Let's get the down conductors, the bonding connections, the grounding, and the surge protection for a full 5 elements of a lightning protection system. Now, when you roll the sphere up and over, it's hitting the lightning protection system and not the building itself. So now we can consider this structure protected from lightning. And I will call your attention to those 2 penthouses. That sphere is rolling up and over them, but they are wide enough that that sphere was going to be hitting in the middle of those penthouses too. So that's a wide flat roof area. We can't ignore those. Even though the risk of counter leader development is lower on a wide flat roof area, it's not zero. So we protect mid-roof areas as well, not just edges, corners, places where the rolling sphere hits. We want to make sure the lightning protection is there. So I'll go through that in a wee bit too, with where the lightning rods are supposed to go. So how does this break down in the code? So the code is written as a safety document to capture the best practices for lightning protection. The major update that we did in the 2020 edition of the CSA B72 code, it changed up things fairly significantly from the 1987 code. The 1987 code itself changed things significantly from the 1965 code, which was the prior version. Prior to that, the US and Canada both had relatively equivalent lightning protection standards. NFPA 780 in the States, NFPA 780, I'm on that technical committee too. It was very similar to what Canada was doing. Ontario had the Lightning Rod Act that was very similar to NFPA 780. But in 1987, the CSA B72 committee had a fellow on it who really thought the European system of lightning protection was solid, rock solid. So he changed up the North American style lightning protection for more of a European style lightning protection in the 1987 code. So for 3 decades, until I got hired up here by my boss and started taking aim at the code to get it trying to update. 3 decades in Canada, we had a completely different kind of lightning protection than the States did. So you drive from here down to Montana, you cross the border, and all of a sudden lightning protection looks completely different. We didn't have to have lightning rods in Canada from 1987 to 2020 because all you needed to do was run a conductor on top of a parapet and call that the strike point. Well, that's not nearly as good for counter leader development as a lightning rod is. So it's not even how they do it internationally in Europe anymore. So we needed to update our code, so we did. So all of this information that I'm going to give you now as to where the lightning rods are supposed to go, it's a relatively new thing in Canada, but only because we finally harmonized the codes cross-border in this B72 2020 edition with NFPA 780. So that's the information I'm giving you now. Before 2020, I would give presentations like this and tell people don't pay attention to the CSA code. But now I can tell you to pay attention to it because it's actually a decent one now. So all that said, where do the air terminals go? Well, they have to be at outside edges and corners. Those are statistically likely places for counter leaders to develop, so it's a good place to have a lightning rod. 600 millimeters is the number you're looking for distance from an outside edge or an outside corner. If we have a parapet coping, for example, the Bow Tower here in Calgary has parapets sometimes that are 30 inches wide. They're about, I measured them at 30 inches, so now I'm having to do the math in my head, 750 odd millimeters, 750 millimeters wide. So in that case, you're not going to be putting the lightning rods on the inside of the parapet like you see there in that image. You're going to have to glue lightning rods to the top of the parapet. Was that done in Bow Tower? No, it wasn't, but that's a whole nother story. When you distribute them around the edges and corners, you want along the flats, you want that lightning rod to be distributed every 6 meters minimum. You can put taller rods, say 600 millimeter tall rods instead of 300 millimeter. You can space those out slightly more, that's 7.6 meters. But in general, for a 300 millimeter lightning rod, you are going to space those out no more than 6 meter intervals along the flat edge of a roof or along the ridge of a long ridge. In the mid-roof, we kind of relax those spacing considerations because of the issue that you don't have a counter leader developing as easily from a flat surface. So then we relax the spacing of lightning rods to every 15 meters. So that's a 15-meter grid on a roof. That's a typo. Ignore that 30 meters in that second item there. 15-meter intervals in a wide flat mid-roof. And then on rooftop equipment, now all of a sudden when you introduce a piece of HVAC equipment on the top of a roof, that is also a great place for counter leaders to start developing. So we were going to put lightning rods on top of those too. And you will see all of this in photographs later on in the presentation. Or right now, as a matter of fact. So here you can see lightning rods on the left-hand picture there. They're spaced every 6 meters. Those are 300 millimeter tall aluminum lightning rods. Like I said before, aluminum is the best material to use in contact with galvanized steel or painted steel parapet copings. You can see there, those are side-mounted bases on the side of the aluminum on the left. On the top right there, you've got an adhesive base that's glued to the top. That's probably to get it closer to the, get it within 600 millimeters of that outside corner there. And then the lightning conductor goes down from there. And then of course we've got the ridge, because there's no metal there, it's just going to be a shingle roof. You can use the copper, which is more conductive. So we tend to use that if we can, but if we can't because of corrosion issues, yeah, we'll use the aluminum. The one thing to note about aluminum versus copper, engineers love to say you have to use copper all the time in a lightning protection system, but I go out and I inspect older systems that used all copper, and I can see that underneath the parapet, underneath the lightning protection material, the parapet's just starting to rust through. So I see that all the time, and I make recommendations for new lightning protection systems that you always have to take the materials into account. The aluminum is thicker and more substantive than the copper. The minimum size for a copper rod diameter is 3/8 of an inch. It's going to be, 10 millimeters. But for an aluminum rod, the minimum diameter is going to be 1/2 an inch, 12.7 millimeters. So if you see the aluminum stuff, it's a bit chunkier than the copper would be, but that's because it's slightly less conductive, so we give it a bit more material. Here's pictures of protecting rooftop equipment. Like I said, you do have to put lightning rods on top of rooftop equipment that extends up outside the zone of protection. You can imagine if you were rolling that 45-meter sphere up and over this building, it's going to hit the edge, then it's going to hit the aircraft warning light, then it's going to hit those mushroom vents there, or those air handling vents. So that's why we want to put lightning protection on top of those. Of course, yes, we do have to get up above the aircraft warning lights because we are required to have a lightning rod extend 250 millimeters, 10 inches above whatever it protects. Occasionally, we will run into trouble with that because, oh, you know what? I'll tell you that later. I actually do have a slide on that. So I'll explain more about that in a few minutes. But you can see that the bottom right there, there's a big air handling vent coming up there. It's protected by 3 lightning rods on it because we always want to stay within 600 millimeters of outside edges and corners. Just putting 1 lightning rod on that big vent is going to leave you probably 1200 millimeters away from the other side. So we want to make sure that we are always leaving 600 millimeters clearance minimum clearance, 600 maximum, sorry, 600 maximum clearance to the outside edge or corner. So if you have to put a number of lightning rods on something to cover it, that's what you do. We do that with big air handlers all the time. If they're 6 meters long, you're going to have a lightning rod at each end and probably at each corner, right, to get within that 600 millimeters. Down in the bottom left, those are big cooling pipes. I bet those cooling pipes are thick enough to take a direct strike by themselves, but you know what isn't is the insulation, the thin metal over the insulation, the heat trace wiring in there. So even though the pipes themselves probably wouldn't take much damage in a strike, the associated equipment and the insulation and stuff, it would. So again, we put lightning rods on top of that. In any case, probably don't want to send lightning grounding all the way down through your cooling system because what's it going to do on the way? Where's it going to flash over? We want to keep lightning on the lightning protection system and not flash through other building systems. So, oh man, I updated this in my, I updated this, but then it didn't sync on the cloud. So anyway, metal bodies of conductance and inductance. I did have a couple of pictures on this. You know what? Tomorrow's session is going to get those pictures. I will briefly explain what a metal body of conductance is. A metal body of conductance is an item on a roof that sticks up outside the zone of protection and requires lightning rods or a connection to the lightning protection system because it is subject to a direct strike. That is a metal body of conductance. A metal body of inductance is, let's say in that bottom right picture there, you've got that skylight that has a little metal trim around it. That is not sticking up outside the zone of protection. It's protected by the nearby tall vent, but it is metallic and it is fairly close to the lightning protection. Now, in this case, they didn't bond it, but let's just say it was close enough to the system. If it's a grounded metal body and it's not outside the zone of protection, there's the potential for lightning to look at that grounded body and think, oh, that's a better path to ground than I've got currently. Let me arc over there. The last thing we want is lightning arcing over to another building grounded system. So lightning could possibly do that if there were another path to ground. So to prevent that, we make a bonding connection to a metal body of inductance. That's just a secondary bonding connection to equalize the potential. Where there is no potential, there's no chance of current flow. So the majority of lightning current will stay on our lightning protection system and go safely to ground. So a metal body of conductance in the parlance is anything that sticks up and requires a lightning rod on it. If it's a thick enough piece of metal, it could take a strike by itself. Sure. Okay. Just bond it to the lightning protection system. But that's a metal body of conductance. We'll come back to that too in the bonding section. In terms of lightning rods, you can also use the architecture. Architects love to make their buildings look pretty. We like buildings to look pretty too, but we also want to make sure they have code compliant protection. Sometimes what that requires is us to work with the architect and the engineers to make sure the lightning protection is kind of built in, and then we can conceal it and it can still be lovely and aesthetic and everybody's happy. So that glass railing, we get glass railings a lot on high-end condo buildings, right? But if you've got a patio in New York City on an upper roof deck and you don't want people to jump over, you have to put a tall screen up there. Make it glass. People get to see the view. It's lovely, except glass isn't particularly conductive, and you don't want lightning striking your glass and shattering it and sending shards of glass going down hundreds of meters to the ground below. So you have to put protection on it. What we do in that case is we put a top rail that's thick enough to take a direct strike on there. Like I said, 4.8 millimeters for using steel as a conductor. We can use that to make a lightning rod too. So if that top stainless steel rail is 4.8 millimeters in thickness or greater, it's going to act as a lightning rod by itself. Then all we have to do is make sure it's grounded properly and at the correct intervals to the lightning protection system. Now it's our lightning rod. It's grounded properly. You still got your glass. You can still see out, but now you still have code compliant lightning protection, and we're good to go there. The top right, that one's the Philadelphia Museum of Art. That was one of my projects, actually. That big bronze sculpture is called an acroterium. They've got those at just about every corner of that big fancy roof. They are considered part of the art. We weren't going to put a lightning rod on top of that because that would ruin the art. But what we did do was just bond the giant bronze statue to the system. Now it's grounded. We've provided lightning protection. You can see the cabling down there in the bottom right of that picture. We provided a network of cabling and grounding all the way down through the structure. And now it's code compliant. And they don't have to see any lightning rods on the ears of that griffin or whatever the hell it was. Anyway, fun project. And the bottom one there is somebody who had more money than they knew what to do with, but they didn't want to see lightning protection on their fancy deck, so they had a custom-made lighthouse lightning rod cast to put out at their deck, so it didn't ruin their view out over whatever very fancy lake that was. I think that was in Connecticut. Lightning rods, yeah, we do have to interface with green roof and photovoltaics because those are happening more and more these days. Sometimes you can integrate it, they can box out so the plants don't grow over the lightning protection. We just did this on the Calgary Cancer Center. They've got a green roof on level 8. So we ran our cabling underneath the trays in which the plants are growing and grounded everything out that way. So we do run across that all the time in green roofs. The only complication to that is when they put in a green roof and the tree starts out small and it's in the zone of protection. But over the years, the tree grows and now it's outside the zone of protection. That's a tough one. Not a whole lot you can do about that. Yes, you can put lightning protection in trees. Historic trees, mainly in the States, get that regularly. You do have to account for the motion of the tree and all that stuff. You can protect trees, but that's one of those small gray areas where, yeah, it had code compliant lightning protection at the beginning, but then the tree got too big. What do you do about that? There's not much I can do. The tree's going to grow. But you can see the solar panels, of course, those suddenly stick up above the lightning protection system. They are going to need protection too. So yes, we do have to put lightning rods to protect solar panels, or I think on the bottom left there, that's a solar heating array. But the only thing that we have to be careful of is not to shade the panels too much, because depending on their design, that could cut out one, it could cut out a whole row. But the last time I had any numbers on this was at a project that covered most of a big Canadian Blood Services roof, and they ran the numbers after the lightning protection went in, and it was doing 0.2% of a hit with the shading to the overall generation capacity of the system. So not that big a deal, but occasionally the PV installer gets tight about that. So we just have to work with them to try and minimize the shading issues. Conductors. Once we've gotten the lightning rods installed, we do have to make sure they're grounded. So that's what we use the conductors for. Once again, you are seeing two different kinds of conductor. You are seeing the copper, you're seeing the aluminum. Once again, we make that decision based on the surface upon which we must install our lightning protection. Takeaway here, you see those are 4 conductors. Top conductor, class 2 aluminum. Next one down, class 1 aluminum. Next one down, class 2 copper. Next one down, class 1 copper. What do I mean by class 1 and class 2? I mean, when we're putting lightning rods on a building, we take into account the height of the structure. 23 meters is the cutoff between class 1 and class 2. So your average home, your average residence, class 1, you can use smaller cabling, you can use thinner lightning rods, less conspicuous, less conducting area, but does fine for a lower building. Once you get above that 23-meter point, now we're starting to look at capturing more lightning strikes. The building's higher, lightning strikes could be statistically more powerful. We're going to use thicker lightning rods. We're going to use thicker cable, more robust cable. That's why we have those two different sizes. And the cutoff for that, 23 meters. The thing that always bugs me is when a building's like 22.5 meters. I'm like, all right, it's class 1, but then they put an HVAC unit on it that's 3 meters tall. I'm like, no, it's class 2. And class 2, that's more expensive material. But that's a problem for me as a designer and a bidder, not necessarily for you all as inspectors. Just know if it's above 23 meters, we're using a heavier grade of lightning protection component. Primary versus secondary conductors. Primary conductor is intended to carry a lightning charge. That's all of these. These are all intended to carry a lightning charge. Secondary conductor, however, that's for secondary bonding. We would use that with a metal body of inductance, not conductance, not one that's subject to a direct strike and needs protection on it. Inductance, something that we could potentially have a flashover to. That's what secondary conductor is for. It's much smaller. It's about half the size of the class 1 cabling there. We use that just for interconnections, equipotential bonding. Lightning current is not supposed to flow on that. So it's a primary conductor, it's a main size, it's going to carry a lightning charge. That's its intended use. Secondary conductor, not supposed to be carrying charge, just an equipotential bond. And that's for those metal bodies of inductance, not conductance. What happens when we run that cabling? Well, we don't want to bend it and we don't want to kink it. Because that introduces resistance into the cabling. So every bend we make has to be a nice sweep. 8 inches radius is the number we are looking for. 200 millimeters. We don't want a tighter radius than that. And we also don't want 180-degree turn. We want to make a sweep. 90 degrees is as much as we want. We just want to make sure lightning has a nice smooth path to ground. We don't bend, we don't kink. Multiple paths to ground are mandatory. We are required to have 2 paths to ground for each lightning rod. So you can imagine those lightning rods there. The cabling goes straight through that base. It's got a path to the right. It's got a path to the left. You've got your 2 paths to ground. Here's the exception. You can dead end a lightning rod with 1 path to ground, only a certain distance though. It can't just be a 30-meter run of a single conductor to ground. That conductor there in the top right, that lightning rod there in the top right, it's running down that parapet and it's going to intersect with the cabling, the lightning cabling down at the bottom. It's probably just glued right down at the bottom of that parapet. That's a dead-ended conductor, and we are only allowed to dead end maybe 2.5 meters on a main roof. You don't want cabling running all the way over, 10 meters away to the nearest main conductor. And then when it touches that, it's got 2 paths to ground. No, you want to keep that dead end as short as possible. And you can't isolate the charge from a building. Some lightning protection equipment manufacturers, especially in Europe, they do claim to make products to isolate the charge from a building. But there are so many grounded systems in any given building. We, in the North American market, don't try and isolate the charge. We have to make those equipotential bonds to keep the chance of site flash low or non-existent, but we can't isolate the charge from a building. You can see the lightning protection cabling is bare. It's not sheathed. I don't know of any, well, I know of one international manufacturer that makes a sheathed, like a triaxial lightning protection cable. We don't use that. In North America, primarily what we use for the lightning protection is a bare copper or aluminum conductor, or tin-coated copper in some instances. So we don't isolate the charge from the building. We have to work with the building, not try and separate ourselves from it. And again, I did mention earlier on, you can use structural steel as the down conductor if the steel is thick enough. And again, 4.8 millimeters, I usually round up to 5, whatever. That 0.2 millimeters doesn't make much of a difference. So 5 millimeters thick, if the steel is that thick, you can have that carry the charge. U-pocket. See this a lot sometimes. You can U-pocket is when you bring the cable down, you come over and you go back up again. We're not allowed to do that. We want to make sure that the lightning protection conductor runs horizontally or downward to ground in all locations. And the only exception to that is you can have a gentle slope up, follow that at no more than a quarter slope, 1 to 4, that we will count as flat for purposes of conductor routing, but we only do that when we have to. For example, coming across a flat roof and coming up to connect to a perimeter conductor. You are allowed to have an upward rise through roof connections. 8 inches is the number for that, 200 millimeters again. That's been in the North American code and in the US code for a long time, and we just added that into the Canadian code too. So it gives us as installers, when we're installing, a wee bit more flexibility. But again, you want mostly horizontal or downward conductor paths or gentle slope risings. Here we go with the connections to structural steel. You can see there on the left-hand side, that's our through roof connection. The roofer puts his waterproofing boot over it. You can see again, we've got those nice gentle sweeps. And then the conductor comes in, connects up to the through roof connection, and there underneath, we're connected up to steel. Then at that point, the steel can carry the charge down to ground. Concealed conductor coursing, yes. A lot of the time we do conceal our conductor within a building. Happens a lot in residences when we're doing a system during construction. The main thing about that is, yes, we have connected we are fastening that lightning protection conductor directly to the wood. It doesn't heat up appreciably in a lightning storm. If lightning gets on that cabling, it's through and done before that conductor can heat up at all. So it's no danger to the wood, even though just as a matter of housekeeping, I would probably get rid of those wood shavings on the left-hand side. That's not going to look good. But yes, you can run conductor on the interior of a building. It doesn't heat up appreciably. The way to think about that is the tungsten element in your toaster heats up because it's resistant. It heats up and it toasts your toast because it's not that conductive. That's fine. Lightning protection conductor, on the other hand, is electrical grade copper or aluminum. And so it's not going to heat up appreciably because it's super conductive. And I think I dropped a statistic, something like 60 to 150 microseconds. Lightning's a very fast phenomenon. It's through and done and grounded out before it even has a chance to heat that cable up. So 60 microseconds later, 60 microseconds of say 20 to 30 kiloamps going through that, that's not going to do a whole lot on a conductive copper wire. So yes, we can conceal in the building. That's no big deal. A lot of the time though, if we're doing a retrofit, yes, we have to do exposed conductor coursing. Also not a big deal because we'll make it look nice. We'll tuck it into a corner. We'll tuck it next to a downspout. Whatever, we'll make it look good. You can see exposed conductors. Exposed, of course, makes it easier for you to inspect because you can see all of it. But when we certify a building through the Lightning Protection Institute, or Underwriters Laboratories can do it also. But we do third-party certification a lot through the Lightning Protection Institute primarily. We have to take pictures of all our concealed conductors and our grounding, and we submit those. We submit an as-built drawing to their engineer. They review everything. Sometimes they will send an inspector out to do an on-site physical review, but we have to keep records. We have to, if we conceal it behind building finishes, we should know what it is. We should as-built it, redline it, and make sure we have photographic records to ensure that, yes, it was done properly. Even though the conductor is concealed behind building finishes and the building looks beautiful now, we still know we did it correctly and we have a record of that. Bonding connections. Excuse me. So these are, of course, two different kinds. You've got primary bonds and secondary bonds. Again, we're going to go back to that primary and secondary conductor. Primary conductor is intended for use as a lightning current carrier. Secondary is not. And the difference for you, and this is something you'll see a lot as you start seeing more and more lightning protection in your inspections, is we use different materials. That pipe bond on the right-hand side there, that's an electrical pipe bond. And it's got that little screw hole. You can put maybe a number 6 wire in that. Our wire is generally a lot bigger than that. So this is a primary bonding lightning conductor, lightning connector on the left-hand side. That's a lightning pipe clamp. It's much thicker. It's a lot more robust. And it has to have about 38 millimeters, inch and a half of horizontal contact between the fitting and whatever it's bonding to. We have much greater contact area requirements for lightning protection than you ever would for electrical bonding. So we use different materials. The materials we do use per UL 96, that is the Canadian Lightning Protection Materials Standards. That U-bolt is listed with UL 96 and CSA as a lightning protection fitting. So that's what we have to use. That's the main takeaway. If you see somebody using the standard electrical fittings in a lightning protection system, most likely it's not going to be code compliant because the fittings we use must be listed for the purpose. And an electrical bond is not listed for lightning protection purposes. Again, primary bonds are for metal bodies of conductance. Conductance, that's again the thing that sticks up outside the zone of protection, is subject to a direct strike and needs a full-size bond with a primary conductor to carry charge. That an example, that's a big warehouse here in Calgary. We bonded that rooftop water pipe. It sticks up high enough, it's thick enough probably to take a direct strike. That's why we used a main sized conductor to bond it and a main sized bonding fitting. Secondary bonds, metal bodies of inductance. They are not subject to a direct strike. The cabling is not supposed to carry any current. So we use the secondary conductor. It's thinner. It's maybe hard to tell on that photograph that I used there, but the horizontal conductor running bottom from the middle of the bottom up to the right, that is a main sized copper conductor. The copper that goes back and connects up to that pipe support, that's a secondary conductor. And we use secondary bonding fittings. That's a picture of one down at the bottom. It's smaller, doesn't have as much contact area as a main bond would, but that's why it's secondary. Not intended for any current carrying. That's merely an equipotential bond. And here's some examples. That top right is a secondary bond. That's an aluminum secondary bonding conductor and fitting, just to that metal pipe there. The rest of these are all main-sized bonds. Sometimes, to be honest, lightning protection contractors will just use main-sized cable for everything. You can save a bit of money by using secondary cable, and it's lower profile, and there's different routing considerations. For example, in a secondary connection, you don't have to worry about horizontal and downward. Because it's only equipotential, you can come down, across, bond it. The connection can be a U-pocket. It can go up, over things. It's okay. It's only equipotential. It's not intended for lightning current to flow on it. That's fine. We don't have to pay attention to those routing considerations I talked about before for the main-sized primary conductor that is intended for lightning current. But these are the exterior connections. You can see to the roof hatch, the water standpipe. There's a gas bond down there. Yes, we do have to bond to the gas. And I'll show you that a wee bit more in future. But yes, these are just examples of exterior bonding connections. And then, of course, we've got the bonding connections on the interior to a steel beam, to the water piping and all that, an electrical conduit there. We do want to make those connections on the inside too. We are required, and you know this, and we are required to have interconnections between our grounding system and everybody else's grounding system, the electrical, water pipe, gas piping, telecommunications. We do have to connect up to all of that. I'll go over that in a bit more detail when I get down to the codes and everything. Well, I'll get into it now, I suppose. Equipotential bonding. Yes, we have to be connected to all of those things. That's not just in the lightning protection codes. It's in the CSA. It's in the CE code too. So we have to be connected to the electrical grounding system. Yes, we have to maintain 2 meters separation between our grounding and an electrical ground or a gas pipe or a buried oil tank or something like that. But as long as we maintain that separation, we do still have to be connected up to that. So yeah, all of those different electrical systems and the metal gas piping, metal water piping, all has to be connected up with our lightning protection system. And that's equipotential bonding. To be clear, we are not using the electrical ground to ground our lightning protection. We are not using the gas pipe. We are not using the water pipe. All we are doing is making an equipotential bond to make sure that everything stays at the same potential in the event of a lightning strike. If there's no potential difference, there's no chance for current flow. Most of the time, We will do this bonding down at grade level or maybe at the main ground bus. But we want to make those connections to make sure that everything is at the same potential. So if lightning strikes, the potential on the whole building rises and falls together, and lightning current stays on our system, does not arc over to anybody else's grounded system. Because when that happens, lightning makes a mess of things. This is mainly
Hey,
for...
Simon,
Yes, yeah.
could I just jump in here for a minute? I don't know if we really defined how we were going to do the questions and that. I saw a couple come up in the chat, and
Oh, okay.
I don't know if you
I
want
was
to jump
expecting
in and
that.
hear them, or should we just wait and you know, just before the break or something, you can review them.
Yep. Okay. Yeah. No. Yeah. Okay. So yeah. So sorry. I was expecting from before. My apologies. The fellow from the safety code said put the hand up. So I was looking for hands, but no. I'm seeing questions now. You know what? Tell you what. I think I'm coming up on the break fairly soon. So I will jump back in at that point and address the questions then.
That's good. We just don't want to derail you.
No worries. No worries.
When you're on a roll.
Yeah. Right. I think we're coming up on the break anyway, so I can go back and address those questions for you, gents. Anyway, this is more for your information as opposed to something that you will run across very often. Lightning contractors hate this stuff. Corrugated stainless steel tubing. It became very, very popular with gas fitters 10, 15, maybe 20 years ago. It's really thin stainless steel tube. And it's sometimes coated, most of the time it's coated in some kind of plastic exterior. It's flexible, it's easy to run, it's much more convenient than black pipe. It bends, it's fine, it's good, great for carrying gas at 5 psi or whatever that is. The only problem is it plays terribly with lightning. If lightning goes nearby and sparks over to this stuff, because it's hard to bond. It's got that like rubberized coating on the outside. It's tough. We have to bond it at the manifold and at whatever appliances it's connected up to. And even if we do that, we are not guaranteed, because if lightning arcs to it, that's what happens. This stainless steel is really thin. All of the rigidity of that pipe comes from the corrugation. So it's super thin. And even the small electrical spark from lightning can cause a hole in it. What happens when you put a hole in a gas pipe at 5 psi and put that hole there with electrical current? You can create a little mini flamethrower. So yeah, this causes fires. You can see that's charred, right? This causes fires. And there was one case in Florida, Texas, where a CSST pipe got punctured by a lightning strike. It didn't cause a fire immediately, but it did fill the house with gas. And then something like a refrigerator compressor kicked on. You got a tiny spark in the house, blew the place up. The walls went out. It went out from the inside out. Everything got knocked over from the inside out. The young man died, and there was a class action lawsuit against the manufacturers of CSST, which of course they fought, but eventually I think they settled it and then had to make lightning safe changes to their CSST. I don't see this a whole lot in Canada. It's mainly used in residential applications, but it's something to be aware of. It doesn't play well with lightning, so we hate seeing this. And if you do find this in a building with lightning protection, oftentimes it's going to have to be bonded a whole bunch just to minimize any chance of sparking over to it. But that's mainly informational. You will rarely see this. Just an issue to be aware of. CSST and lightning do not mix. Now we're getting down to the bottom here. And this, of course, you're a lot more familiar with. Soil conditions are going to be a major factor, of course, in what kind of grounding system we design. But one of the takeaways here is, once again, if you look at that picture in the upper right, you've got the acorn nut that's good for electrical grounding, and then you have the much chunkier and more substantial lightning protection ground. Once again, we have to have about 38 millimeters worth of contact, 1.5 inches of contact along the axis of that rod to make sure that's a lightning protection fitting. Much chunkier. So lightning grounding and electrical grounding are two separate animals. yes, we can do, that's only for a clamped connection. We can still do exothermic welding. You can still do high press grounding. That's also okay for lightning. But if you're using a bolted fitting, it has to be bigger. It has to be more substantial. It has to be listed for the purpose. Once again, back to the UL, you see the UL stamp on the lightning fitting there. It is listed for the purpose of lightning protection. And there is a standard that applies to the manufacturers of those. Yes, we can do a buried ground ring. We can do a buried ground ring with rods. We can do ground plates. We can do radial grounds, which are just conductors run away from the building in a trench and then backfilled over. We have to do a ground ring on any class 2 structure. So if it's over 23 meters, we must do a ground ring. Didn't used to have to. So older buildings are kind of grandfathered. We're not going to go do a ground ring grandfathered in on a retrofit for a high rise in downtown Calgary or Edmonton. That would be cost prohibitive. But on a new structure, if it's going to be over 23 meters, a class 2 building, we are going to put in a ground ring. Here we go. These are some examples of it. I think that's the, that's the bedrock under Telesky. They dug down far enough under Telesky that they hit bedrock and then they had to chisel. So you can't really drive a ground rod into that. So what we did was we put ground plates down, we embedded them in ground enhancement material. Then we run a ground loop conductor around the outside, bonded to the rebar, and then they just backfilled the concrete over that. I think we were underneath the mud slab. So that is 100% permissible for lightning protection use. That's our ground underneath Telesky. Guarantee you it's been used a few times. Telesky's been up a while and it's tall enough that it's going to take a strike or two each year, I think. So in any case, that's permissible for grounding in a high rise. You can put the grounding in a loop in the foundation. And over 23 meters, of course, you're going to have that loop down there. Most of the time, we put that underneath the lower parkade. You may or may not encounter this in your electrical inspections, but if you see it when you're out there to check the electrical ground before it's backfilled, that's what we did. We put a lightning ground loop in and ground plates. And ground enhancement material is just, it's like a carbon slurry that you slap over a ground plate or a ground rod or whatever. It does seem to do the trick, which is quite helpful for getting the low resistances you might want. We managed to get, I think, under 25 ohms in the basement and the ground of Telesky, which is pretty good for on bedrock. But we did use a whole lot of ground enhancement material on our plates. The grounding materials, it's all the standard stuff that you've already seen as an electrical inspector. Our ground plates have to be a bit bigger. We have a minimum size for the ground plates. They're bigger than standard electrical ground plates. You can see that they're partially buried in the top. Ground rods, of course, we can use copper or stainless. Usually it's copper clad steel. We just use the same off the shelf stuff that you can get at e-call or whatever. So 3/4 inch, 19 millimeter by 3 meter copper clad steel. That's our standard product. Ground plates, you can use copper or stainless. And the choice of material really depends on soil conditions. In an acidic soil, we might use stainless. I've used stainless ground plates for pumping barges and corrosive Suncor holding ponds and stuff like that. So just really depends on where you're putting this stuff. Ground loops are going to be copper or tin coated copper. The only material we do not use below grade is aluminum. That's because aluminum is going to corrode much faster in an acidic soil. In fact, aluminum, we want to keep, by code, we want to keep it about 1/2 meter up above grade. We want to make a transition to copper or tin-coated copper to go into the ground, 450 millimeters, 18 inches above grade per code. So aluminum does not go below grade. That's the only material we do not use down there. Of course, you've all seen this stuff before. Again, exothermic welding is fine for us. We tend only to use exothermic welding in the ground. We do not use exothermic welds at roof level because roofers don't want sparks all over their stuff. That's not too good. So we will always use bolted connections at roof level. Every now and then we see a spec where an engineer wants everything welded, and some older lightning protection systems will have welds at roof level, but we don't recommend it and we don't use it anymore. So you will rarely run across that unless it's a very old building that somebody's re-roofing. Here we go, back to the interconnections. And I do want to clarify this point. You all know this already from your electrical inspecting, but yeah, I figured it was worth it to go over the code in detail here. Separated by 2 meters from each other, interconnected with a conductor. This is a deliberate interconnection made of a material prescribed for grounding conductors, sized as prescribed, and protective from mechanical damage. In the case of lightning protection systems, interconnected in accordance with the above, at, or below ground level. So we have to make our interconnection with the electrical ground at or below ground level. That could also include an electrical room on the ground floor with a main ground bus. We are allowed to make that connection there. That's fine. You cannot use lightning protection down conductors and grounding electrodes for grounding of electrical or telecom equipment. We see cellular antenna people trying this all the time. They'll ground out to our stuff. Not so much Rogers or Shaw or the big ones, but smaller firms and other antenna installers will try and ground out to our lightning protection cable at roof level. Bad idea. Bad idea. Just if lightning does get on that, it can energize the antenna and have to fry out coax wires and circuits and all that stuff. Don't ground to our stuff. The grounding electrode for a lightning protection system should be dedicated for use solely by the lightning protection system. This is not meant to preclude use of a ground loop conductor, just for interconnecting everything. We will connect to those. We'll come down, we'll drive a ground rod, we'll connect to the ground loop conductor. That's an interconnection. That's not us using the ground loop conductor for our lightning ground. Also, in any ground loop situation, you're also going to have an electrical ground grid, and that's going to be separate. That's going to be over near the transformer, or it's going to be underneath the main electrical room or whatever. That's fine. We will connect to that. We'll stay 2 meters away. We'll connect to that, but we're not using that in any sense as our lightning protection ground. And this is a question that I fielded actually just this past year, and it was in April, I think, that the stand data, I'll pull that up a wee bit later on, that the stand data was issued. This is a question I got earlier on this year from an electrical inspector at a facility down in southern Alberta. He was worried that we had lightning protection coming through the roof, which we're allowed to do, and run down through the building. And I believe on the other side of that, cold form steel strut, we did have a conduit there, but to get to it, we looped kind of down, and there was some incidental contact between our lightning protection conductor and the steel. Now, because that building steel is going to be grounded out and interconnected at some point with the electrical ground, he was worried that this constituted an interconnection. It does not, because an interconnection needs to be deliberate. It needs to be made with a conductor. We have incidental contact with the electrical ground and other grounding systems all over the place. All over the place. Like when we mount a lightning rod to the top of an HVAC unit, that's making incidental contact with the electrical grounding system. When we make a connection up to, say, a gas pipe at roof level, that's also an interconnection because the electrical ground is continuous with that. A water pipe, a conduit, an electrical conduit, if it's near enough our conductor that we have to bond it like a metal body of inductance, that's incidental contact too. But that is not the deliberate grounding interconnection that must be made at or below grade. All of those are incidental. All of those are not specifically supposed to be the interconnection with the electrical ground. So that doesn't count as the interconnection. Those are incidental contact. So what we did, because we wanted to work with this electrical inspector, we went back and we sheathed it in flexible poly conduit, and removed that source of incidental contact. There were still many, many others, but we wanted to act in good faith, and so we covered up our lightning cable on the interior and we removed all question. But just so you know, this incidental contact, that's not our connection. It's supposed to be made of a material prescribed for grounding conductors, sized as prescribed, deliberately interconnected. All that other incidental contact anywhere else on the building, that's not the thing. That's not what we call our grounding interconnection. Surge protective devices. You may or may not run across this. A lot of the time, those are going to be installed in the gear, in the transformer for sure, or the main distribution panel. That's often built in by the manufacturer. That would be type 1 versus type 2. And in any case, in CSA B72, whereas 780 has surge protection as part of the normative text, I couldn't convince the code panel in Canada of that. So it's in the informative section. It's not required. We are not required to put surge protected devices in, although we always recommend it, and we will do it for a residential structure where we're sole contractor and there's no other electrical on board. But yeah, surge protection devices aren't required as part of CSA B72, but they are an integral part of lightning protection. So we should be aware of that. The thing to know about surge protection is that they are listed for lightning protection purposes. You can have surge protection devices for switching transients and for power line fluctuations and things like that. But a lightning protection surge device is something different. They are tested against specific surge waveforms, 20 kiloamps for a main electrical surge protective device is the current they test against. So those are tested at the factory against a lightning waveform, 20 kiloamps of per phase of discharge current. That's how they're tested, and so they are listed specifically for lightning protection purposes. You've got type 1 and type 2 SPDs. It just depends on the location. Type 1 is more for the main distribution gear. Type 2 can be put on smaller sub panels and distribution panels. But UL 1449 is edition 5. That's generally what these things are listed to. And then CSA has its own stuff about type 1 and 2 SPDs. And of course, you've got all the antenna, coax, telephone wire, twisted pair, all of that stuff. UL has standards on those too. Again, you will rarely be called upon to inspect that kind of thing in terms of looking at lightning protection systems, but you have to be aware of it because it is an essential component of lightning protection. And of course, that's just a good idea. You can have multiple tiers of surge protection, and every data center does. We do a lot of protection for data centers, so they have both type 1, type 2, and then point of use. Lots of people try and use that too as an electrical safety thing. You know what, folks? I was going to go through the safety codes and how they apply, but I'm thinking it may be a good time to stop and take some questions from the chat. I was going to do a 15-minute break after this section here, but I could probably stand to get up, walk around, use the washroom, and answer your questions before I do that, though. So let's go back up and see. 236 meters, bow tower, good. Okay, all right, so let's go down here and see these questions. Oh, slides are out of sync. Did that issue get fixed? Oh yeah, well, that could just be me. Okay, it could be tech difficulties. Yeah, sorry. Yep, I did. I did make edits to this morning that never synced in the cloud for me. So I'm using a different computer now than I was editing on. You are correct, K Hood. Theft of grounding conductors is a concern. Where theft of grounding conductors is a concern, we will try and use a concealed system. We'll try and put the stuff inside the building. Failing that, if we cannot, we will put our conductor inside a rigid conduit. We are allowed to use metallic conduit. We just have to be sure to bond it to the lightning protection conductor that goes through it, top and bottom, to prevent any inductive choking effects. Yeah, because lightning current going through there, well, the magnetic field moving through so quickly induces a current on the metallic conduit, which then that could interfere with the lightning current flowing through. So we make sure we are electrically continuous with that conduit top and bottom. That does help. The other thing I don't think you will run into very much though, it's from the specific section in B72 on telecommunications equipment protection, and Rogers and Belshaw. Rogers and Shaw, I think, are both on the CSA B72 committee, and we permit galvanized steel to be used as a grounding conductor in the telecommunications section only. So our main method of stopping theft is concealing the conductor inside a building or in conduit, or even poured into a concrete pour for a reinforced concrete building. The primary conductors are larger than the secondary conductors. I'm not sure what you mean by loosely bound. The weave is roughly the same. They're made on kind of the same machines, but they are supposed to be fastened the same way. They're supposed to be hauled down the same way. Every 900 millimeters is actually the I'll get to that a bit later on when I'm talking about inspectability. That's our fastening schedule for lightning conductor. But yes, primary conductors are larger, Clark, and secondary conductors are roughly half the size. You see CSST everywhere. Oh, bummer. 23 meters for a ground ring. Yeah, that's 23 meters is the cutoff between class 1 and class 2. For class 2 structures, we want to make sure we have a ground ring to interconnect the lightning grounds. That's mainly a function of equipotential bonding. In fact, for taller structures that aren't structural steel, we have to interconnect the lightning down conductors every 60 meters just to make sure we don't develop too much of a voltage between it.
Hey,
Sorry?
Simon.
Yes, sir.
Yeah, that's me to ask a question, Clark, here.
Yeah.
When asked to clarify the 23 meters, what dimensions is that? Is that down, around? Is that the height of the building? Is that the size of the ring?
Oh,
What is
yeah,
that 23 meters?
Yeah. Once the building gets above 23 meters tall, that's when we need to put in a ground ring for it. So, yep, no problem. Good. Sorry. Thank you for clarifying your question. Yeah, 23 meters tall and above, we put a ground ring in. And yeah, as I was saying, so for example, Stantec Tower in Edmonton, it's much bigger than 23 meters. So it has a ground ring. Well, of course, the whole Ice District complex has a ground ring way underneath the parkade there. But Stantec Tower also has a number of equipotential loops at intermediate levels because if you have long lengths of down conductor with the current potentially flowing down them, you can develop voltages between them, between roof and grade, such that it's possible for lightning to flash off onto another grounded system. So we interconnect those down conductors every 60 meters at average intervals of no greater than 60 meters on a very tall building. But I don't think I have that anywhere in the quiz. Don't worry too much about that. That's almost always concealed in concrete pours and you wouldn't see it very much. But yes, above 23 meters, we use a ground ring to interconnect all the grounds. Oh, neighbor's house, lightning damage, right by the gas meter. No, we don't accept galvanized ground rods for the grounding electrode because those will deteriorate too quickly, Ed. Galvanized steel for ground rod, I think it used to be allowed under the old CSA code, but we no longer accept it because they are just going to rust away too fast. And iron oxide is not particularly conductive, so the less conductivity we have in contact with the earth, the less efficient the dissipation of lightning current. Ooh, okay, delayed by about 20 seconds from the speaking. Is that a common issue that Gordon's having? Is everybody having a wee bit of a delay here? Okay, yes. I can review inductance and conductance again. Inductance is for secondary bonding. That's to prevent flashover from the lightning system to another grounded system. Secondary bonding connection, secondary bonding conductor, only for equipotential. And you don't bond everything on a roof. I'll go through that a bit more later when I'm talking about the inspection procedures. But inductance is not subject to a direct strike. It's inside the zone of protection. It just happens to be nearby a lightning conductor. And so to prevent flashover, we bond to it to make an equipotential bond. And conductance is sticking up outside the zone of protection and requires a lightning rod. Structural beams connected to lightning current mitigation system. Yes. if we use structural steel as the down conductor, then it's okay to hang other grounded systems off of it, to hang conduits, to hang sprinkler systems and all that stuff. Again, because lightning is such a fast event, the current is going to go straight as possible to ground. It's going to follow the most direct path to ground, which it'll split. It will go through multiple steel beams. We ground steel beams down at the bottom at 18-meter intervals. And I'll go through some of this later on. But yes, the lightning is through so fast in a matter of microseconds. It doesn't do much to other grounded systems that are incidentally connected to that steel. No delay, no delay, no delay. Okay. 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 All right. So I believe I've answered all the questions I've got. Please, by all means, let me know if you are having issues still. But I will allow a 15-minute break, and then we'll move on, and then we'll talk about the safety codes and how to inspect lightning protection systems. I really appreciate your attention so far, folks. I know I ramble on a lot, but I'm trying to give you your money's worth and give you as much information as possible. Please feel free to drop more questions in the chat. I will address at appropriate points. Thank you for your attention. I will see you back here at around 10:30 or shortly thereafter. 10:33 I'm seeing. So thank you, folks. Morning again, folks. I'm gonna give people a couple more minutes to get settled back in, and also shut my door because the rest of the office doesn't need to hear me waffling. Well, hopefully this is the actual slide I wanted to show you about metal bodies of conductance and inductance, and because those are very specific terms to the Canadian Lightning Protection Code. They don't appear anywhere in NFPA 780, and they're holdovers from the 1987 version. They used conductance and inductance. We just kind of retained them, but you can see here that antenna. It sticks up out the zone of protection. It is subject to a direct strike, so we call that a metal body of conductance, and it has a lightning rod on it. You see up at the top there. So that's the conductance. Inductance is a potential flashover point, and that's the lower photograph. Oops, get back there. That's the lower photograph. Those two pieces, they're well within the zone of protection. You can see a higher roof behind them. They are within the zone of protection. There just happens to be a conductor going across that roof to connect out to the lightning protection on the other end of the parapet that would be behind the photographer. And those two items are within the zone of protection. They do not require a lightning rod, but they are right next to the conductor, and they are electrically grounded bodies and potential flashover points. So we've connected those up to our lightning protection cable as a metal body of inductance. So that's the slide I was looking for, but I finally got the cloud sync to happen. So this is good. I will now forward on. And 42, one more minute brings us to 15. I get to recaffeinate, although that doesn't appear to have been a problem so far. Larry can attest. When I gave a version of this to the Electrical Contractors Association in Edmonton at their annual meeting some months ago, I don't stay still. It's very difficult for me to stay still when I'm presenting. So this Zoom stuff is difficult. I wandered all over that room. Anyway, all right. Okay, so now lightning protection and Canadian safety codes. We are going to dive back in. And then we're going to look at the stuff that's really important for you, how to inspect this stuff. So now you know kind of what the lightning phenomenon is. You've got an idea of all the different bits and pieces that go into a lightning protection system. You've seen a bunch of different pictures of this, that, and the other thing from lightning protection. So let's look at the codes and how they apply. So this is all the applicable codes in North America. The one that's most important for us, of course, because it's mentioned in the Alberta Safety Council stand data, CSA B72, 2020 edition. I am currently in my second term as chair. CSA only allows you 2 terms as chair. So hopefully before I get the boot, I can get one more edition pushed through of this. Man, I'm telling you, code writing, it's boring, to say the least, but crucial. Because the step we took from 1987 to 2020 was a huge one. Finally got Canadian lightning protection code into the modern era, harmonized it with NFPA 780, which is now in the 2023 edition. So now lightning protection is supposed to look pretty much the same across the border. And because you can't fix and find everything, and in the application of a new code, you'd start getting questions from people about this and about that, and you realize, oh, I could have clarified that. Oh, no, I forgot. Oh, God. So I really would like to get one more edition pushed through before I'm kicked off the, not kicked off the committee, but kicked out of my chairmanship. I've got a running list going. And honestly, you all can help with that. If you do a read through and you find things that are unclear and you don't understand, please bring it to my attention. I want this document to be as clear as possible. And it's code language, so, sometimes you have to phrase things a certain way, but you all have a place in telling me where I went wrong, where I didn't phrase something in as clear a way as possible. So honestly, I do not mind. I take feedback well. I take criticism because, I've been married a couple of times. I take criticism fairly well. That was more information than you needed about me. UL 96A, that's Underwriters Laboratories. They are one of the inspectors of lightning protection systems. You can get third-party inspections from them. LPI, that's the inspector that we use, the Lightning Protection Institute. They are also really good. And they're working on right now getting accreditation for their apprenticeship program. So we might be able to, in future, get an accredited lightning protection apprenticeship program up here in Canada also. So that's potentially coming down the pipe. We'll have to see. Here is our shiny new code. There's the old 1987 code. It was written in 1987, and then it just kept getting reaffirmed. You're seeing on that little image reaffirmed in 2008. It got reaffirmed again in, I think, 2013, and then one more time in 2018. Reaffirmed just means we don't want to make any changes. Thank you very much. But now, this is our spiffy new code, CSA B72 2020. No, lightning protection will never go back into the CE code. I very strongly doubt it. The CE code doesn't want lightning protection. CSA already has a lightning protection code now, so it's never going to go back in there. Not as far as I know. That would be a big surprise to me if it ever was. I believe it's going to be maintained as a separate document. Mainly because lightning protection isn't a requirement, isn't a hard requirement, except in very specific situations. Whereas the electrical code is pretty much a hard requirement in all jurisdictions. I don't believe there's not going to be any merger there anymore. Did it used to be in the CE code? Because I know there was a 65 B72 and a 1987 B72, but I didn't know if it was ever in C22. Anywho, here's our nice new code. This is the one that's going to apply. This is the one that, as an electrical inspector, you would go to and look through that for what the requirements are for the systems you are looking at. Yep. Yes, exactly. A standard is we're listed as an installation code. The US NFPA 780 is a standard. So it's a little bit different down south of the border, but if you choose to put lightning protection in Canada, it must be in compliance with CSA B72. This is why it's the National Building Code. I know we've got the Alberta edition, and the BC edition and all that, but really, it's the same thing, and nobody has ever, to my knowledge, at least in Western Canada, which is my jurisdiction really, nobody's ever tried to mess with this section of the National Building Code. So that's just followed through into Alberta and into BC. When you do install lightning protection, you don't have to, but when you do, it should be or must be in conformance to B72, because we don't have provincial territorial legislation anymore anywhere. Ontario used to have the Lightning Rod Act, and occasionally I see legacy specs calling for compliance with the Lightning Rod Act in Alberta. We don't have one. We've never had one. It's always just been B72. Here's the thing about building code. The reference to B72 in the National Building Code is to the 1987 version. See that second inset down below. That's the table of, stop it. That's the table of references. So the National Building Code still refers to the old one. I personally, as the chair of the technical committee and CSA internally, my liaison at CSA, we've both put in requests to the NBC to update this reference. I believe they do, well, I've been told by CSA that they do a mid-cycle update to references in the National Building Code. It's not a full revision of the building code. It's a mid-cycle update that just updates any references that are outdated. And I believe this year, later this year, well, in fact, if not by the end of the year or early next year, the NBC is going to update this table. So the B7220 is now the addition. However, as you'll see in a couple of slides, Alberta has already taken that step and said, no, B7220 is what we need to inspect to. Just for your reference, you've got a few other codes and documents that apply, that mention lightning protection in Canada. Nuclear facilities, this is kind of important. You don't want nuclear power plants blowing up because of a lack of lightning protection. So yes, you do have to put protection on all of those things you see in the inset there in nuclear power plants. Yes, Clark, by all means.
Sorry to harp on this again. So this is now listed in the building code that this has to be inspected to. Is that going to move to electrical code to reference this standard then?
You know what? I'd have to go look at directly in the C22.1, but it's in the building code, and I think the building code starts and ends with the reference to B72.
Yeah, but we can't enforce a building code.
Cover it.
I think there seems to be a gap here.
Okay. How could we? You know what?
In Alberta, there's a stand data out for that,
Yes.
for actually to use for electrical to be able to enforce the lightning code for that.
Yep.
So we'll be able to do that in Alberta.
Yeah,
There's
you'll
a
see
stand
that.
data out already.
Yeah.
Yeah, but as a permanent measure, it would be good to move that clause to the electrical code somewhere.
I'm not sure that somebody's made that reference to move it to part 1 yet.
Fair. Thank you.
Yep. Which isn't to say it couldn't be done. But that's above my pay grade is all I will say to that. When we're talking about the NBC and the CE code, my involvement with CSA is solely through B72, and I have made requests for changes to other documents to do with lightning protection, for example, the fire code, and I did consult with both N393 and 293, which are the two nuclear facilities and power plant things, to talk to them about what they could do based on our update. So I've been in touch with those code committees, but I don't do much with, well, I don't do anything with CE code or NBC. But like I said, I have requested the update, and we'll see what shakes out with CE code and NBC later on. Anyway, not that you will run across this very much because we don't have nuclear power plants in Alberta, as far as I know. So just for your reference, nuclear facilities should have have to have lightning protection. And by the way, we're just finishing up a project in BC, or just finished a project in BC that was creating medical isotopes using I think a synchrotron reactor, which is creating nuclear products. So we did have to put lightning protection on that as part of this N393. This does not, by the way, apply to hospitals that simply use those radiation byproducts. For example, your X-ray machine or whatever, like anything like that. Any of the imaging that hospitals use, they are not required to have lightning protection on them. Those do not count in terms of facilities that produce, handle, or store nuclear substances. So this is strictly for things like places that produce the nuclear isotopes, or power plants, or nuclear waste storage, or what have you. That does require lightning protection. Not that you will run into this very much, but the Department of Defense, as you might imagine, doesn't want their explosives blowing up. So they put lightning protection on bunkers, hangars, control towers, comm facilities. I am currently in the middle of a project for national defense to rewrite the standard because it hasn't been touched since a good long time ago. You see that 1977, or no, wait, it's a 2004 edition, I think. Anyway, I'm helping DND rewrite the standard for the modern era, so there's going to be a new one of that. You probably won't be inspecting bases much, so don't worry too much about that. What you will run into sometimes is the City of Edmonton requires lightning protection on certain facilities, or at the very least a risk analysis. City of Calgary does not quite yet. I keep having a conversation with the chief electrical engineer at City of Calgary to try and get them to at least match Edmonton, just come on, as a friendly competition kind of thing. We should have design guidelines similar to or better than, shouldn't we? Anyway, AI, Alberta Infrastructure, does also pay attention to lightning protection. They require a risk analysis. I know the fellow that maintains this design requirement document, and I think he's going to update it now to the new CSA B72 now that the stand data is out. So the risk analysis that used to happen in the 87 version, not particularly robust. We reworked the entire risk analysis section. Now it harmonizes with 780, and it's a bit more technical in nature and doesn't give you those weird numbers like 3.5, 4.5. Don't worry about that too much. That's on the engineering side, less on the inspection side. Here is what applies to you. This is the stand data. So the Clarence Cormier, best of luck to Clarence. He's off to the Maritimes, I think, back to where he grew up. Then somebody else is going to be taken over as the provincial electrical administrator. But he and our chief building inspector, David Chang, I guess, they put this together and ran it through the Safety Codes Council and got buy-in from multiple stakeholders on this, and everyone agreed that it's a good idea to make sure lightning protection is done properly. And I'll tell you why this was an issue for me personally, and us as an industry in general, is because lightning protection goes on roofs. Roofs get redone every now and then. When roofs are redone, often the roofer doesn't bother to call the lightning protection contractor. So they'll yank the stuff off and put it back on the way it was. It has never once in my entire 25+ year career been put back the way it was. Not once, which is a problem. You are now materially compromising the safety of said building. Don't do it. So this was part of the discussion within my industry as a whole. And I brought this to the attention of Clarence and David, and they agreed and they took it to Safety Council. And so now we have a requirement for an electrical permit for lightning protection. So it shouldn't just be anybody yanking stuff off and putting it back on, because it's a safety system. I'll put it to you this way, and this is how I explain this to engineers all the time. In buildings, it's code to have a sprinkler system. So in the event of a fire, that sprinkler system goes off and stops the fire from spreading before it can do damage. It's a passive system. It sits there and does absolutely nothing for you unless there is a fire. Lightning protection is a substantially similar in function safety system. It sits on the building, doesn't do a darn thing unless the building is struck by lightning, in which case the lightning protection system captures the bolt, conducts the electricity harmlessly to ground, and provides a safety function in that regard. Those two systems, both preventing fire, ostensibly, right? But the lightning protection is a passive system, and so is the sprinkler system. Those two things act to protect the building against rare but potentially catastrophic events. So that's how I tend to look at it. So don't mess with it. Is there an electrical permit? What we have done, Art, there's a question in the chat as to, is there an electrical permit? whenever we're subcontracted to an electrical contractor, we just say, hey, you have to add lightning protection into your electrical permit. If we're contracted after they've got the electrical permit already, then they have to mod their electrical permit to include lightning protection. But
Actually,
anyway,
City of Edmonton requires a standalone electrical permit for lightning protection, because if you add it into the same as the main electrical permit, it's usually not the same contractor doing the work. So we have to limit it.
Oh, yeah.
So it goes strictly to that contractor.
uh,
We've issued our first one already.
oh, okay. All right. Awesome. Good. That's good to know. Yeah. And we ran into that doing some work up for an EPCOR facility recently. So, yep. So you have
Well, Jerry, do you guys require a master then when they pull that permit or not? Probably not, eh?
Probably not. We're not going to actually get one, probably, because I don't know that there's anybody, there are even electricians doing that work. So right now on this particular one, PCL pulled it. So they do have a master,
Right.
but they're pulling it for the lightning protection contractor.
Yeah, us. we were the lightning protection contractor.
Okay.
But yeah, that's a good clarification though. Thank you, Jerry. So this is what has dropped lightning protection in your laps, ladies and gentlemen. It's because now this is a quality control issue to make sure that lightning protection is done right. You wouldn't let just anybody take apart your sprinkler system and put that back together the way it was. You want somebody qualified because it's a safety system. So this is why we've got this now. And now it's in your lap, and now we're talking. Now I'm driving myself hoarse telling you all about lightning protection. Nope, we did this already. I'm skipping this slide. Let's go on to how this means, what you are going to be looking at in the field. So if you didn't get this, send somebody an email at EIA. I can send it again. I believe my contact information was on some of the preliminary documentation that was sent out for this. So you can always send me an email too. I will send you back a copy of this checklist that I'm pulling these issues out of. Not get the checklist. Okay. Well, it's available. Please get in touch with me or EIA. I know I sent it over to Dan. I think I sent it over to Dan and Laurie. So there is a copy floating out there somewhere. And if you don't get it eventually, feel free to get in touch. Honestly, feel free to get in touch with any questions about any of this. Like
Simon, it's Larry. I'm going to interrupt you for 1 sec.
Yeah.
Rather than people constantly putting comments in the chat box that they did not get this or they did not get that, just respond to the email where you were sent the Zoom link and just say what you did not receive and it will be sent to you. So just respond to the email where you received the Zoom link. And obviously all of you received the Zoom link, because if you didn't, you wouldn't be on the call. So just respond to that and identify what you were missing and it will be sent to you. Sorry to interrupt, Simon, but I just wanted to clarify that.
Sounds good, but I sent out the Zoom links, Larry, and I never got this checklist either. So we'll get that fixed up.
Right. Well, then what I should do is send that checklist off to Dan and Laurie. Make sure that can be distributed as necessary. Anyway, I do have a whole checklist. It's a 1-page sheet. These are excerpts I'm pulling out of it, and so I'll go through these checklists and give you kind of an idea of what you might want to look at if you are called upon to inspect the lightning protection system. So air terminals, here's the list of things. Now, what I did when I created this whole checklist sheet was I went through and I found the most common things that happen to lightning protection systems, the most pertinent aspects of the code. I tried to distill it into an easy format for my installers when they're out on roofs and doing inspections. I use it when I go out on roofs and do inspections. And it just tries to distill everything in the code into an easy yes/no. So hopefully this is used to you. Once we get it distributed, I will email that out tonight. So hopefully on Saturday's presentation, everybody who's participating can be like, oh yeah, I got that. I can follow along. Because that's what you all sound like in my head. Anyway, air terminals, are they intact? On the left, you have an air terminal on the top of Stantec Tower. So I'm also giving you the view from the top of Stantec Tower, just in case you ever wondered what that was like, at least in one direction. I think that's facing north. So now you know what it looks like. Top of Stantec Tower facing north. That air terminal is perfect. It is absolutely intact. It's on top of a cooling tower. It's actually, this is an example of a dead-ended air terminal because it dead ends down to the bottom of the railing where the main loop conductor is, and it bonds into that. And from that point, it has 2 paths to ground, which every air terminal has to have. That's looking good. And you can see the intact air terminals beyond it on the other side, around that perimeter. I'm pointing at it like you can see me pointing. Okay, I usually do this in front of audiences and point to a screen. That's not happening here. But if you look at the middle, this is also Stantec Tower, that middle. Window washers knock our stuff over all the time. And yes, we have tried. We tried to put a spring-mounted lightning rod on there. But even at that, it depends on how hard they hit it. It depends on how long it's in contact for. Sometimes those will break too. Yeah, that's why there's a safety wire. It's not going to get knocked over and fall off the edge of the building and go down 30 stories from this balcony level to the sidewalk, but it is busted and now it needs repaired. And then in the top right, that's just another air terminal on the same level as Stantec Tower, and that's just completely busted off as opposed to just bent over. And then in the bottom right, there you find an example of how not to repair a lightning protection system. That's not going to do the job, just to be clear. Although if you do look closely at that, you'll find one of the common failure points on a lightning protection system. That base is cast aluminum, and it's got a little stub that sticks up and the lightning rod screws down on top of it. You can see an intact assembly on the left-hand side there. Same kind of stub, same kind of adapter. Air terminal screws into that, but that is a common failure point. It snaps at the base. The stub is now stuck up inside the adapter at the base of the air terminal. We have to replace the whole base there. There's not much you can do at that. And at that point, you probably have to replace the lightning rod too, because aluminum has this strange capacity to bind to itself when it's out in the field and exposed to the elements for a while. So sometimes you can't even screw that lightning rod back off again. The aluminum is just chunked and bound on there. Okay, yes, indeed. Dan will send the checklist out when he gets it. I can send that out right after I'm done this.
I just jump in here, Simon. I just got it from one of our administrators, so I'll fire it off to everybody right now.
Sweet. That's easy. Look at that. Results, folks. Air terminals. Are they installed on all roof areas that require protection? Here's a tale of 2 hospitals, folks. On the left is Red Deer Hospital. It's got some lightning protection on it, but it is not fully protected. Only some of the roof levels have it. The upper roof levels, they have done additions to the hospital. And there you see that white clad penthouse, or that white clad roof area has absolutely 0 lightning protection on it. So on the checklist, you check no, air terminals are not on all the required roof areas. Meanwhile, on the right side, you can see that's South Health Center, and that penthouse there definitely does have lightning protection on it. Well, almost the whole hospital has lightning protection on it. You know, that was one of our contracts back in the day. So yep, that penthouse most definitely has lightning protection on it. So you can check, yes. Do they extend high enough? The magic number here is 250 millimeters. 254 if you want to be super specific, I guess, but I don't, because I don't care about that 4 millimeters. That's just the metric conversion of the NFPA 780 10 inches. We converted everything in CSA B72 to metric. I keep talking to my colleagues on the NFPA code. Like, come on, man. I know you like the convenience of 20-foot spacings, 20, 40, 60, 80, 100, but how hard is it to multiply by 6? Come on, 6, 12, 18, 24, 30. It's not that bad. You get used to it. Can you just, for me, go over to the metric system? Come on. I'm sure you're hearing I was born in Scotland, right? I have a weird accent. But I spent 25 years in the States working down there. So my accent's a mess. And now I'm in Canada, so I say hey at the end of my sentences every now and then. I'm just an absolute disaster accent-wise. But I grew up on the metric system. And then I had to move to the States when I was 13 with my family. And then I had to learn that there were, I didn't know up to that point that there were 5,280 feet in a mile. I had to learn all that stuff, inches, feet. I was on the metric system. And then I moved up to Canada after, 25, 30 years of working professionally in the States and doing the inch, pound, foot system. Now I have to relearn the metric system because I forgot it. So anyway, so if I say inches sometimes, That's why. Anyhow, 10 inches, 250 millimeters. On the left-hand side there, you've got an aircraft warning light, which are required to be the tallest point on a structure. We're required to be 10 inches above that with our lightning rods. So on the left, there you go. On the right-hand side, however, there's the lightning rod out at the end of that parapet that one of our installers had to shimmy out and put on there and didn't enjoy the process. But then you've got that aircraft warning light right there, and the lightning rod only sticks up a wee bit above it. Now, the number in the old code, the 1987 code, was 50 millimeters, 2 inches. You only needed 2 inches of clearance above any particular thing with a lightning rod. Because we harmonized the codes, now we're back up to 10 inches. And now this picture on the right doesn't have the required clearance. There are some exceptions to this. Because lightning protection isn't a hard requirement, I mean, it kind of is, because once you've decided to put it in, it has to be in conformance to B72, although the building code still says B7287 until later this year, maybe. But then, the people that don't know that and don't really care about it, building mechanical equipment designers, the engineers that design those things, design those with absolutely minimal clearance over the stuff on the roof. So that warning light on the left-hand side there, we're only sticking up 2 inches above that because that's all the clearance the building mechanical equipment operator would give us. The engineer designed it in, and we physically couldn't put the lightning rod up higher than that. They would not let us. So when it comes to who wins in the code, often we lose to the structural engineer or the building mechanical equipment engineer, and we just can't put our lightning rods up much taller. So sometimes when you see an installation like this and we don't have that required 10 inches of clearance, that's why. It's because they didn't allow it. The picture on the left is city center down here in Calgary. The picture on the right is on top of the Bow Tower. And they just did a huge BME renovation. They would not let us put lightning rods on top of those air units or those vents because they would just get knocked over. We said, look, we'll put spring mounted rods. They said, nope, because it didn't even have enough clearance to allow the spring to flex. They had like 2-3 inches of clearance over the tops of those vents. So we had to use a short stubbier lightning rod as an attachment point. And there's nothing else we can do about it, right? We lost that argument. So that is one thing to see. If you see at the very top of a building something that doesn't have the highest point, if it doesn't have that 10 inches of clearance, there might be a reason for it. And it might be something the lightning protection contractor had zero control over. So in that case, we had to flex to accommodate the existing conditions. Tall air terminals must be supported. So anytime you have a lightning rod that's over 2 feet, 600 millimeters in height, you are required to support it at a point no less than half its height. You can see on the left-hand side there, that's a hospital here in Calgary that had an old system. They decided they wanted to protect that security camera. So they put a really tall rod up there, but it has no support. So technically that's not in compliance with code. Has it survived a good number of years? Yeah, it has. It's doing its job, I guess, but it's technically not in compliance with code. Meanwhile, on the right-hand side, there is a tall air terminal, and there are specific lightning protection fittings and tripods and things that you can use to hold those up. And now all of a sudden, it's in full compliance. Those tripods, by the way, are an absolute pain in the ass to make look good. You have to bend it right, and then you have to bend the feet and you glue it. That's a pain, but this is what we have to do. You'll see those. I've seen a bunch of those in military applications where they want extra protection, higher rods to protect wider areas and all that stuff. So I do see that a lot in military applications. But for the most part, for most of the buildings that you will be inspecting, you're only going to see those 300 or 600 millimeter lightning rods. Are the air terminals close enough to the corner? 600 millimeters, folks. That's the number we are looking for. On the left-hand side, one of our recent projects in Calgary, big warehouse for an unnamed internet retail giant. I don't know why they make people sign non-disclosures for these. It's not like anybody else is building warehouses that big in Canada right now. But Anyhow, yes, the lightning rod is within 600 millimeters of the outside corner. Whereas on the right-hand side, that's a building I inspected a number of years ago, where somebody that wasn't a lightning protection professional put in the lightning protection system, and that is not 600 millimeters away. In fact, it's slightly worse because in the old code, in the 1987 code, which is the one that applied at the time I inspected that, you had to be 500 millimeters away from the outside, so 4 inches closer to the edge. That one's getting on double that. Yeah. Now, this isn't to say that electricians can't put lightning protection in. As you see, an electrical permit is required to put lightning protection in these days in Alberta, and an electrician could pull a permit and do it themselves. The problem is, SAIT and NAIT don't teach it. They don't teach lightning protection yet. Depending on how the building codes go, I may have to actually get a hold of SAIT and NAIT and put together a course for them to tell people or tell the apprentices what lightning protection is all about. But it's not covered. It just isn't covered. It's not covered in electrical engineering school for the most part. The only reason I know what I'm doing in it is because I fell into the industry when I was 19 or something like that, or 20, and I've been in it ever since. So you have to either know somebody or follow into it or take a job in it in order to learn anything about it, because nobody trains you in it. My qualifications, I'm a certified master installer designer with a fancy brass card from the Lightning Protection Institute. I took 4 tests, progressively harder, and then a 5th test to get my designer qualification. To get my master installer, I also did years worth of field training in the actual installation work. So I've seen this from both sides. I've done it from the installation side, and I've done it from the engineering side, and that's my qualification. But again, that's only because I fell into the industry. It's certainly not covered in electrical apprenticeship programs. Yes, it would be a good case for stamped engineering drawings with these types of installations. However, you also have the problem where electrical engineers don't know much about this either. We often consult with electrical engineers and do the drawings for them, and they stamp them. Or we have an engineer that we work with that will review our drawings and stamp them for us on a contract basis. But I do this all the time. I see a tender come through, and there's a basic lightning protection layout put together by an electrical engineer who's read B72 and said, oh yeah, I see how this is supposed to go. And then they put it together. I'm like, all right, cool, good starting point. I'm going to redesign this thing though, so I can bid it. I know that what I'm bidding is a code compliant system. I'm not counting the number of rods the engineer's wanting. I'm going to double check. I'll look at the architecturals. I'll figure out what it needs. And then I will do my own design, do the takeoff, and that's what I bid based on. So I know for my own peace of mind and my boss's peace of mind that I've covered everything that needs to be done to make a code compliant system. That's just the way I've worked and have worked for my entire bidding career. I always have to do a redesign. So engineers aren't really trained in this either. Let's go on. Are they spaced correctly? On the right-hand side, you can see that's another one of those warehouse jobs. And yes, every 6 meters, we've got that lightning rod sticking up. On the left-hand side, though, those rods they're not 600 millimeter rods, which would allow for 7.6 meter spacing, but they are shorter than that. So they would have to be spaced every 6 meters, and they are most definitely not. Those are actually closer to probably 8, 9, 10 meters apart. And that was that's another hospital job here in Calgary that I did an inspection on. Lots of these pictures, by the way, are just from either jobs that we have done or jobs that I have inspected. So I've seen lightning protection go wrong many, many ways. So I have lots of pictures on record of the way things aren't supposed to be, because when I write the report for a building owner, for Alberta Health Services or whoever, I have to be able to say, here, it doesn't meet code because X, Y, and Z, and here's the proof. This is one you probably won't see a whole lot. Eave lines above 15 meters tall are required to have lightning protection on them. This particular building, I don't think the eave lines were quite that high, but I just wanted to show you what it looks like to have air terminals at an eave line. But the reason for that is that even on a slope roofs you can protect with just a line of lightning rods down the middle if the slope is over a certain amount. depending on the width of the building. If it's a small building, the slope can be 1/8. If it's a larger building, the slope can be 1/4. But otherwise, if the slope is greater than that, you can just protect it with a line of lightning rods down the ridge. Now, the taller you make that building, the more likely it becomes that lightning will bypass any lightning protection on the ridge and hit the eave line, because that's also an edge and a corner. So we want to put lightning protection down near there once we get above 15 meters high to the eave line. So here you can see that's just an example of what it looks like, but I don't think you will run into that very much. It's a rarer condition. We just happened to do it on this structure because that's what Sask Water wanted. Their engineer, they wanted lightning protection all around the roof, so that's how we did it. But it gives me a good example to show you what protection at an eave line looks like. And then is it on the rooftop equipment? This is another thing I used to see a lot, but I'm starting to see less as code develops and moves on and installers change their practices. In the 1987 code, you were permitted to simply bond to rooftop metal equipment with a single conductor and call it a day. You can see that in the right-hand picture there. That's a high rise down here in Calgary. Just a single metal strap that's bonded to those vents. And then lightning, presumably if it struck those vents, it would go through that metal strap to the lightning protection system. The only problem being with that, as even a code practice back in the day, is that you are absolutely not guaranteeing that the lightning current is going to follow that metal strap. That's a 1-inch wide copper strap. Okay, good. It's conductive. That's fine. Lightning will follow that. Some lightning current will follow that, but you are also providing a steel duct and a steel vent and everything that's connected to this fan, this vent, where there's a fan blower underneath, maybe there's an electrical ground there. You can't guarantee that the lightning current is going to all go on that strip. So now with our B7220, we require a lightning rod on top of the rooftop equipment with a dedicated lightning conductor. Is some incidental current going to run on that ducting? It's possible, it's probable. However, we are also giving it a highly conductive path to ground through our lightning conductor. So the majority of lightning current is going to follow that. And whatever current is left to ground out through the HVAC, through the electrical ground that might be connected to it, is going to be nominal, it's going to be small, and it's not going to be enough to cause any damage. Conductors. Let's go through the conductor checklist, which I guess went out to everybody. So maybe now you're following along. Here's my checklist for conductors. Are they intact? Well, on the left-hand side, yes, those conductors are looking fantastic. They are fastened at the correct intervals. They're good. They're looking solid. Meanwhile, and this is incidentally why I occasionally bitch about roofers touching our stuff. That rat's nest up there was part of a re-roofing project at liquor warehouse here in town. And the roofer took all the stuff off the roof and piled it up there. And we gave, that's a sore spot, because we gave the company that owns the warehouse a price for us to put this all back on properly and replace with new, because you can't do anything with that stuff. And we could try and unkink all of that and like get it all looking nice again, straighten out the lines and make it look solid, but it's going to cost more in labor than it is to just toss that stuff in the scrap pile and put whole new stuff in. The labor to try and unkink that and make it look good isn't worth it. Just put new on at this point. So we gave them a price for that, but then they decided that they didn't want to pay that. So they got somebody that wasn't as qualified in lightning protection to just try and put that stuff back on. And it's still kind of hanging off the building and not right, but that's their prerogative, because lightning protection isn't an exact code requirement. They are now out of compliance, but nobody's calling them on it because this didn't have to be inspected back when that happened. And then the bottom there, that's another roofer special. Normally we would use a clamp or a fitting to connect two pieces of cable, but sure, yeah, you can just wrap it around and call it conductive or connected. That's not how it's done, boys. So this is why the whole issue of people not qualified in lightning protection keeps coming up for us, because I see this all the time in inspections I do. Ooh. Conductor checklist back up. You should have a copy of this in your inbox, but there you go. Make sure they're intact. Is the coursing correct? The dead ends I was talking about. you're only allowed so long on a main roof. I'll have the picture for that slightly farther down. Are the bends okay? Are they installed in the mid-roof, and are they fastened correctly? So are they intact? Yep, yep. Are they listed for the purpose? This is another thing that occasionally happens. Remember I mentioned way back when I was talking about conductors that you won't find a sheathed conductor? Is green 2 acceptable in terms of lightning protection? Probably. In terms of sheer carrying capacity and opacity, yeah, it's probably fine, but it's not listed for the purpose. It's used all the time. In oil and gas, that's what they use a lot of the time because they've got hydrogen sulfide floating around, and the bare copper is going to corrode faster. I'm not going to tell Suncor how to do their job because it's absolutely certain that lightning protection copper conductor can corrode very fast under environmental conditions like that. But for most of what you will run into, no, that's absolutely fine to have bare copper conductor. Now that left-hand picture there, that was on a job that an electrical contractor was doing the install based on a design and layout and materials that we gave them. Then they ran out of materials. So they weren't using our conductor that we'd sent them, and they didn't call us for more. They decided they'd just go out to your local e-call or EB Horsman or whoever and get themselves some aluminum grounding conductor. And then they put that in there. But the problem is that's not a listed lightning conductor. So you want to make sure it is. And the reason that the way you can tell, at least on a newer system, is we are required to have conductors with a UL sticker every 10 feet. Every 3 meters on a listed lightning conductor, you will see a sticker that says UL 96 and maybe the manufacturer's part number. So we use listed lightning conductor. That aluminum stuff wasn't a listed lightning conductor. So that's just one other thing to pay attention to. Cheaper. Oh, there it is. Cool. Go away. Sorry, next slide. Here we go. Are the conductors coursed correct? On the right-hand side pictures, yes, the conductors are coursed correctly. They have a gentle upward slope to ground right there at the top. They have nice smooth bends, a nice sweep radius there. But then on the left-hand side, on the bottom, you've got conductor coming straight up the wall to ground. And then at the top, you've got the conductor making a big U-loop. A bend radius is too tight. It's making a 180-degree turn. It's also, if you look in the bottom right there, right by the conduit, it's also kinked right over that I-beam flange. So that's just absolutely not cool. And here again, not that electricians can't install lightning protection. You absolutely can. Electricians are fantastic. No number of things, no amount of things, any amount of things, sorry. Like there's lots of stuff electricians do that I absolutely cannot because I'm not bloody well qualified. However, if they've never been trained in lightning protection, you're going to see things like that. The devil's in the details in any trade. And so these are good electricians who did both of these installs on the left-hand side. They just don't know the specifics of the lightning protection code. So when I did the inspections for both of these, I said, oh no, you got to change this out. You can't do X, Y, and Z. Here, keep the bends nice and nice sweep radius. You can't go straight up the wall. You have to come up at an angle, but nothing against their qualifications as electricians. They were really good electricians. They just didn't know the lightning protection code. And that's not their fault because nobody ever told them. Conductors dead-ended here. This one's kind of hard to visualize sometimes. I did talk about it way up top with the lightning rod that was glued on the parapet top. But here's an example from the Bow Tower. Hey, now you're getting the view from the top of the Bow Tower too. I'm just taking you on a tour of all Alberta's tallest buildings. But see down at the bottom of those vent fans there, there's a short horizontal run of cable that comes over to the main conductor across the roof. We call that a dead end. The drop from the lightning rod at the top all the way down there. We don't worry about the vertical component of it, but that horizontal run there over to the main lightning conductor can't be more than 2.4 meters or 8 feet, whatever it is. So we want to keep those dead ends short. Meanwhile, that antenna over there, meanwhile, that antenna there, that's dead ended with a single path to ground that goes probably 6 meters back to the main conductor. So that one was a non-compliant dead end. Are the conductor bends acceptable? Well, on the left-hand side, not particularly. I don't think I need to tell you that looping the conductor around a lightning rod a couple of times isn't a valid connection. That one, ladies and gents, is another roofer special. I'll show you a few more roofer specials before we're done here, but that one's a particularly egregious case of the roofer not knowing what to do with the lightning protection. Oh, I'll just loop it up here, that'll hold it in place. That's not really how it's done, folks. But anyway, on the right-hand side, now you see some acceptable conductor bends. One thing that will happen with somebody who's not fully trained in the lightning protection code is they'll make a real tight bend at the corner. They'll just jam it right in there because they want it to be as neat and clean as possible. That's just not how we can do it. That adds too much resistance to our cable. We want to make sure it's a gentle sweep. Mid-roof conductors, are they installed? On the right-hand side, yes, they are. There's our air terminals in the 15-meter grid in the mid-roof. You can see there. Those mid-roof conductors go at 15-meter intervals. And for long roofs, really big roofs, if they exceed 45 meters on any given run for that mid-roof conductor, we need to interconnect that again in the opposite direction. So any grid on a roof is going to be 15 meters one way and 45 meters average spacing the other way, no more than 45 meters spacing. Whereas on the left, that's a massive arena up in Sherwood Park. We recently renovated it, so now that is code compliant, but that's a picture from before it was. Big wide roof area, didn't have those mid-roof conductors, so we had to flag that in the inspection and go back and then repair it later on. Are the conductors fastened appropriately? Roofer specials again, folks. They pulled the lightning protection up and put it back the way it was. That doesn't look like the way it was. The cable is just coiled up on the roof. It snakes all over there. There are no fastenings. The reason we fasten our conductor is there are some significant electromechanical effects. If you shove 20,000 amps of current through a conductor in a matter of 60, 70, 80 microseconds, at the joints and at the bends, there is a significant force that happens, an electromechanical force. I've seen this at lab scale. There was enough force to just yank a conductor directly out of the clamp when the clamp wasn't fastened properly. So yeah, you want to fasten it down because you don't want it whipping around in the event of a lightning strike. That's going to cause damage to the conductor. It's going to pull components out. It's going to do damage to the roof, perhaps. That's why we fasten the stuff down. It's not just to make it look good, although yes, it has that function too. It's also to prevent the electromechanical effects from causing damage to other components around. And on the left-hand side, you can see there's no fasteners whatsoever. And you've got a lovely snake going on there at the parapet in the bottom picture. But over on the right-hand side there, you can see a nice, tight, clean install on a penthouse parapet wall there. You fasten it properly, you make it tight, and it's not going to whip around in the event of a strike. Down conductors and grounds. So this is another one you'll run into. And I assume at some point everyone will eventually get a copy of B72220. That would make CSA very happy. I'm driving sales here, CSA, you're welcome. But the down conductors and grounds, and you'll see this if you eventually give the document a read through, they have to be installed at average perimeter intervals of 30 meters or less. The reason we do this is because, again, I've tossed around 20,000 amps of current. That's just what we test surge protectors at, but it's not by any stretch the most powerful lightning strikes on record. The most powerful lightning strikes on record go north of 200,000 amps. So 200 kiloamps of current going through. That's an awful lot of current. So the reason we have multiple paths to ground for every lightning rod is we want to divide that current up. Maybe we could shove 200,000 amps of current through a single down conductor, but we don't want to try. We want to give it as many paths to ground as possible so that current can divide, and then we take it down to ground. Functionally speaking, yes, Martin, I will get to you in just a second. Functionally speaking, lightning tends to go through the closest two down conductors. It will split and go through the closest two down conductors. Some might run through the other down conductors farther away, but it just wants to get to ground as fast as possible. That's why we don't want to spread our grounds out too much. We want to give them 30-meter intervals at most, and then the lightning will divide if it strikes and go down the two closest down conductors the majority of the current. Yes, Martin.
So just a question, because in your little checkpoint there, it doesn't seem to show 12-016 where our code talks about, because I'm assuming a lot of this is coming from your standard, but our code says also that where lightning down conductors are installed, electrical wiring shall, where practicable, be kept at least 2 meters from such conductors. So we cannot have any of our equipment near your down conductors, but that doesn't seem to be on your checkpoint list that you have for us inspectors.
You are correct. That's well, the operative word here is, and I've been writing codes for 20 years now, I think. The operative word here is where practical. That's every code writer's that's every code writer's wiggle room right there. Where practicable, because we understand very well that you can't always. Sometimes you don't have the space. That 2 meter distance is, I'll get to that when I get to the bonding part. That 2 meter distance is usually considered the maximum flashover distance for lightning current to do to a different grounded system. It's very rare for any flashover to go farther than 2 meters. So functionally speaking, what that means is that we'll generally just bond all grounded bodies within 2 meters of our conductor to our system. So there's equipotential. So jump flashover doesn't happen. That's probably where that number came from in CE code. But again, we've got that wiggle room with where practicable. Even when we're on the outside of a building, it's entirely possible that, 300 millimeters away on the inside past the curtain wall, there's going to be some electrical wires in there. There's no real way. There's no real enforceable way to always keep a lightning down conductor 2 meters away from every other electrical wire. Just can't be done. That where practicable is there to give everybody some peace of mind, because you can't enforce it. You just can't. You do your best. You don't deliberately route conductors right next to. I've seen antenna installers on roofs just like zip tied their coax conductor to a lightning cable. That's terrible. That's a really stupid idea, because you just guaranteed that you're frying out your system with that in the event of a lightning strike. But where practicable, it's the wiggle room. It's the thing where how do you enforce it, right? It wasn't practicable. Okay, done. So yes, that's a great call there, Martin. But yeah, that's any code writer's wiggle room right there, is that where practicable. Whenever you see that, somebody was hedging their bets. So we'll just go through, take a look at, does a building have enough down conductors and grounds? And here's an example of a submittal document that I put together for a data center project here in Calgary. I always do this on my drawings, and this isn't necessarily something you'd be seeing. You don't see my submittal drawings. That's something for the engineer. But I called out here, building data, protected perimeter is approximately 270 meters. So if we are required to have a down conductor every 30 meters maximum, I'm going to need 9 on this building. And that's what I'm showing. Around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got more than I need. So I always try and put 1 extra in just in case. But 270 meters divided by 30 meters on the average, I'm going to need at least 9 down conductors. I've given it 10, so we know I'm compliant here with code. That's something that you would probably know after a walk around of an overall roof, just counting the number of. But it's something that it would probably be helpful to interface with the lightning protection installer to get a copy of their shop drawings while you're walking around and looking at things. At least that gives you something to work off of. So if you're inspecting one of my jobs, for example, I'll happily send you a copy of that shop drawing submittal or our as-built, and then we can walk around together even, and I'll show you what we've got. You can see that we have exactly enough grounds. All this stuff is there. It can be scaled off. Are they intact? For the most part, you should be able to tell. If it's exposed, yeah, you can just do a visual verification. The down conductors and grounding is intact. Although on the left-hand side at the top there, yet again, folks, it's another roofer special. They did a re-roof on a very bougie school in the Calgary region, and just left that down conductor hanging at the top and never put it back on. Then when we went out to inspect, we were like, they made your building significantly less safe. What is going on? In this particular instance, I remember the roofer called me and said, hey, can you give me a quote to put this back on? And, I gave it a couple of days before I could get back to him, give him my workload. And I call him back and he's like, oh, no, never mind, we got it. And I was like, all right, cool. But I'd already gotten the documentation, and the roofing consultant had said, put lightning protection back in conformance to. It was not. It wasn't even close. I've used a couple of pictures from that install because it was particularly egregious. It was just terrible, the condition he left it in. Disconnecting grounds, not putting fasteners back on, not actually connecting the cable, but wrapping it around itself to make a connection that's not valid. It's not a listed fitting. Down at the bottom on the left is another school project. The perimeter sidewalk had pulled away from the building and basically yanked the cabling right out, just snapped that copper cabling right there. So when we had to go back out and repair the grounds on that too, just double check, are the down conductors and grounds intact? Bonding connections. Although, to be fair, a lot of the time you wouldn't know because let's say Stantec Tower again, I showed you some pictures from that. The down conductors are tin coated class 2 copper poured directly into the concrete columns. The electrician, Western Electrical, did that for us. They ran the conductors up for us in the concrete column pours, poked them out at the top, then we put the through roof connectors on it and bonded it to the steel at the top. But you would never see that because it's poured in. The intermediate loop conductors also poured into the concrete pour. There's no way you can inspect that, but that's why we have qualified installers and good electricians, and we keep records and we take photographs. So you won't be able to inspect it, but you should be able to interface with the installer or the electrician or whoever took care of the down conductors and confirm with them that it was done. They'll have photographs and stuff. We need to be able to prove it to certify our systems. So we try and keep good records about that. Bonding connections. Here we go. There's that 2 meters, Martin. Installed for all metal bodies within 2 meters of a main conductor. And this is a rule of thumb. There is a method in B72 for calculating the bonding distance. The bonding distance is calculated based on the height of the building, the distance to the nearest down conductor, how many down conductors are close by. In reality, very rarely does a lightning protection contractor calculate the bonding distance. Although for a low structure with down conductors close by, the bonding distance could be as low as 300, 450 millimeters. So anything over that, you don't need to bother with. Practically 2 meters is a significant jump for a lightning bolt current on a main conductor. So if you bond everything within 2 meters, you're usually fairly good. That gets you all your major bodies of inductance within within the bonding distance. If you just bond them, call it a day, you don't have to worry too much about that. Have we bonded as required to the other grounds, the electrical? Have we bonded the water piping? Have we bonded the gas piping? These are the things to look for. There's some non-intact bonding connections. Roofer special in the top left. That I think is just wear and tear and maintenance that somebody wasn't paying attention on the bottom. That's a Calgary high rise. I think they replaced some rooftop equipment and then never replaced the bonding connection. So that's a thing that does happen a lot in maintenance. Whereas on the right-hand side, of course, there we have the bonding connections. They're nice and solid. And that's no problem at all there. Are the bonding connectors acceptable? On the right-hand side, sure they are. Those are listed lightning protection fittings. I know I keep saying that, but it's a thing. Because over on the left-hand side, once again, very qualified maintenance electricians, but they used a pipe bond that wasn't listed for lightning protection. And I mean, come on, look at that, gents. Look at that, folks. There is a set screw for like a number 6 cable there. That fitting isn't designed to hold a close to 2-watt lightning conductor directly against a painted metal pipe. That's not quite an acceptable bonding fitting, okay? That split bolt fitting on a piece of strut on a piece of galvanized curb, Also not a listed bonding fitting for lightning protection. Did the cable fit through it, at least in that case? Yes, it did, but that's not a listed lightning protection fitting. Split bolts, we never use because they're usually not big enough for our stuff, and you have to squish our conductor to get them in. Are the metal bodies bonded at all? There goes the roofer special on the left. They just course the cable right between all those metal bodies, some of which are metal bodies of conductance and should have lightning protection on them, but do not now. That lower vent on the right-hand side there, that's a metal body of inductance because it's going to be in the zone of protection from those higher vents to the left there. But that wasn't bonded the way it should have been. And of course, on the right, you can see metal bodies that have been bonded in conformance to the code. So yeah, are they bonded at all? That's another thing to look for. And again, 2 meters, if they're within 2 meters and they're bonded, good. If something's 2.5 meters away, probably doesn't need bonded. And one thing you will occasionally see is we sometimes go overboard on our bonding. We'll bond to rooftop drain covers. Are those grounded? Maybe, but we bond to them anyway if we go right by just to cover all our bases, even though we know that underneath the stormwater drains are jointed with rubber insulators and stuff like that. That's not a continuous path to ground necessarily. We'll still bond it occasionally just to make sure there's no question. Are the other grounded systems bonded? You'll have to double check that. The only time this might look different is if you have a gas distribution system that has a cathodic protection current run on it, then they do not want us to bond directly to their gas piping. And we always have to bond on the customer side of the meter. We don't want to bond on the other side, mainly because on the other side, sometimes that's where they have the cathodic protection. They're running current, so if we ground it to the supply side of the meter, we'd be draining off their cathodic protection current, and that's going to make a mess of things for the gas company. So they don't like us to do that. Always bond on the customer side. If we must bond something with cathodic protection, there are other options. We wouldn't be using a listed fitting like that. We would use something like a spark gap bonding connection. I've never used one, so I suspect you will never see one. It's just an option. But if you do inspect a system where you see something a little odd about the gas pipe bond, talk to the installer. They may have had to use a spark gap. I doubt you will ever have to, though. There, of course, we bond up to the electrical ground on the right-hand side. That's on the interior of a kind of a residential facility. We just bonded up to the electrical ground wire at the ground floor. And then there's a standard main ground bus. That's from a big hospital in Vancouver that we did some work on. So the lightning protection came back and the grounding connected up on one of those nicely arrayed. Good work there by MPE Electrical. Non-compliant systems. Now, I don't suspect you will see this very much, but I feel like you should know about it anyway. Oh, is there a question in the chat, or is it just a chat in the chat? Why the transition from aluminum to copper, primary and secondary pass? Good question. Yes. The question, we're not allowed to put aluminum and copper together. If we do, we have to use a bimetallic fitting that separates the two metals, because otherwise they'll eat one another and cause corrosion. That's no good. Of course, we talked about why we use certain materials in a lightning protection system. The aluminum we'll use galvanized steel, painted steel, in contact with aluminum rooftop equipment, stuff like that, aluminum housings. And then the copper is the main conductor for down conductors. On a roof, we usually glue copper to a roof. We don't use aluminum, mainly glue to a roof, because it degrades faster in the presence of standing water. So if we have puddles on the roof, we're not going to be running aluminum through that, especially here in Canada. We get snow loads and moisture is in contact with that roof for a long time sometimes. So we'll use copper in those locations, and for the down conductor and for the grounding, because no aluminum below grade, that kind of thing, right? 823 does not list a rod as an approved electrode. Oh, that's totally an approved electrode. In 823 in which standard?
720. This one here, yeah, B72. Sorry.
Oh, we list rod specifically. It is in there. I know that. So it could be in a different location, But yeah, definitely rods are permitted. We are allowed to use ground rods. That's our standard product, right? I'd have to switch out of here to switch over to look at B72 and tell you exactly where that was, but it is in there, I promise you. Now, how common are roof leaks, Vitaly, after attaching clamps to roofing membranes? Roof leaks are, we only use approved products with a roof. We will never use a non-approved adhesive. We have a sign-off form that we send to the roofer or the roofing consultant saying, can we use this? And if not, what do we use instead? We do not cause a roof leak because we do not want to hold the warranty. The warranty is the roofers. That's why we use adhesives that are approved. And if we are going to attach to a parapet coping and our screws might penetrate the roofing behind it, we get sign off from the GC or the roofing contractor or the roofing consultant. We never compromise the roof warranty. Done that once or twice. Well, companies I've worked for have done that once or twice over the course of the years, in which case we're paying. So we do not want to pay to repair a roof. So we will always use products that somebody else has signed off on and said it's okay. For exterior galvanized and painted steel surfaces, nope, we are required to use aluminum. It says copper shall not be installed on exterior galvanized and painted steel surfaces. So that leaves aluminum. That's our product that we use on those surfaces. So
Simon, Art has his hand up there. I believe Art has a question.
Oh, sorry. Yeah, go ahead, Art. Yep.
Yeah, this is Michael. So a while back you were talking about where your down conductors were running and you had main conductors within 450 millimeters. So, and you said you were talking about the equipotential bonding.
Mm-hmm.
Will that be done with a secondary conductor or a primary conductor?
The way B72 is written, I believe the equipotential bonding, if it's a secondary connection to a single item, you can get away with that smaller cable, smaller connectors, no big deal. If you are doing a loop of equipotential conductor to interconnect all the down conductors, that has to be a main-sized cable. Good question. Yeah, that's definitely something to be clear on. Main-sized cable, ground loop conductors.
So do you have to bond to the ground or to the gas line? Are you guys bonding to the gas line in all cases? Because we bond to the gas line in the electrical code. We have to bond to the gas line.
Mm-hmm.
So do you bond to it as well?
Yes, yeah, we do actually. That's the way NFPA 780 is written. So that's the way now CSA is written. We have to bond to gas line, electrical, water pipe. We have to put our own bonds on there. Unless all the grounding is put together a main ground bus, then we are permitted to make a single connection to the main ground bus. But the way the code is written, we have to use lightning conductor and lightning fittings to make those bonding connections. So yeah, functionally speaking, yeah, we should be making sure we bond it with our conductors, our fittings. And is it redundant? Yes, it kind of is. But that's how we do our quality control to make sure that we are absolutely connected up the way we should be.
You also have to bond to the primary, our primary ground, right?
Your primary, what, sorry?
You bond to our service ground as well, right?
Yes,
So,
one location, yeah. Mm-hmm.
In one location.
Yep, and we have to be 2 meters away from it and all that. So, yep. Yeah. So we always want to make those bonding connections. And again, that's just to prevent flashover to other grounded systems, right? Okay, so I'm going to go through this quickly because I don't expect you will see very much of this. We have specifically excluded some alternate lightning protection technologies from CSA B72. Those are early streamer emission systems and charge dissipation or charge transfer systems. What the hell are those, you may be asking? Well, they aren't independently validated scientifically. People have done lab scale studies with these things, and the manufacturers of these things will tell you that, yes, we have studied these and inside and outside and high voltage labs and stuff. The only problem is they don't have any code support, either in Canada or in the US, or in fact, really internationally. There's no scientific validation that's consistent for these things. And they kind of played fast and loose with some of the laws of physics when they were making their marketing claims back in the day. ESE, early stream emission, a single mass system, kind of look like flying saucers. We see something like this trotted out by a new company once every few years. Remember I talked about the counter leader coming up from edges, corners, lightning rods, tops of trees, whatever. Lots of places for ion channels to start that upward counter leader. The ESE device people say that they have a device that helps to emit a counter leader sooner, that moves faster up to connect to the downward stepped leader earlier. So it protects kind of an umbrella because it connects up to that stepped leader sooner and higher up, it protects a wider area. In fact, I saw one of the manufacturers of these things claim something like a 200 something meter protection radius for their device on one of their submittal drawings. That's absolutely impossible. There is just no way. I've seen these things fail multiple times myself with my own eyes. I've seen them fail, or I've been on buildings where they got struck when they had one of these things and they weren't supposed to be struck. That thing was supposed to capture the lightning strike, but the building itself took the hit instead because they didn't have these within 600 millimeters of the outside corners and all that stuff. They're usually on a single tall mast that sticks up and it's supposed to protect a big wide area. It just does not. That's the problem. Here's an ESE device on a house. That house next to it that got struck was well within the claimed protection radius, and it still got struck, got the damage, burned. That ESE device wasn't doing the job it was saying it was going to do. These things are awfully common out in Asia, and Malaysia in particular. Oddly, I don't know, they had a ton of them. So these manufacturers sold a lot out there. So that's where a lot of these failure pictures come from. Is they installed these all over the place. I was on a tower in New York City that had one. It was one of Trump's towers, but he'd lost it in one of his divorces. So one of his ex-wives owned the tower, still had his name on it. I don't know why. Anyway, I'm up there, I'm standing here and I'm looking up at the ESE device on a mast, the ESE, early streamer emission, single mast system, whatever you want to call it. And I'm looking up at it and, you know, there it is. Okay. And down underneath there was a fried out panel, charring on the wall where the lightning current went through. But I looked just to the left from the ESE device that's supposed to protect this big wide area. And then at the end of the parapet over there, the only reason chunks of stone hadn't been blasted off and fallen 150, 200 meters to the street below is because they'd recently put a waterproof coating around it, fiberglass reinforced, and the fiberglass was actually holding the stone together, but it was falling apart because the lightning hit the stone at the edge. Wasn't supposed to, because this mast system was supposed to protect the whole damn building, except it didn't. That's why I don't recommend these things, and you won't see very many because there's no code support in Canada for them. These are other buildings that had ESEs on them. They got struck. They picked the concrete up from the ground where it hit and put it next to where it got blasted off, just to show you, yeah, this is what happened. So ESE devices don't work. This is what I saw this in the past year. Enhanced lightning protection system, controlled leader triggering. That's they're talking about it in science language, just to be confusing. But I had to write this engineer and be like, I know you got this spec from one of the manufacturers of these things, but you can't install these in Canada. Here's why. And then I got one of my manufacturers to send the whole package over why ESE devices are crap, why you shouldn't spec them. They don't have code support anywhere in the world, as far as I know, except last I checked in Czechoslovakia, which isn't a country anymore, but you know, whatever. If you see these, they are non-compliant. There's a couple of buildings in Calgary that a couple of high-rise condo buildings that have at least one that I know of that has one of these. And I'm just counting down the days until I get struck and fries something out there. And then they call us out and say, why didn't our lightning protection work? I'll say, because it's not lightning protection. Bye. Dissipation systems, you won't see many of these. Occasionally they get sold to oil and gas. I doubt you'll see these, but they're supposed to drain the energy out of the air so lightning doesn't strike at all. They're supposed to prevent a strike, period. Just doesn't bloody well happen. Remember I showed you the picture of the 15-kilometer long lightning strike way back at the beginning? You think you can drain enough energy out of the air to prevent something that started 15 kilometers away and traveled all that way to get to you? You think you're going to prevent that from happening? No, you really aren't. So these things are useless. Anyway, you just have to, the manufacturers of these say you're supposed to put an NFPA 780 compliant system on and then put these bottle brushes on top of it. Why? Just leave the NFPA 780 system alone. It's doing its job just as it is. How do we know these things don't work? Well, because we bloody well tested it. We had to. If we as a lighting industry were saying, no, those things don't work, and the manufacturers were saying, yes, they do. Okay, well, let's test it. So here we are in New Mexico. They put a bunch of these things up on poles. The ESE device that was supposed to capture lightning strikes sooner and protect a wide area, it didn't get struck. The dissipator that's supposed to bleed the energy out of the air and not get struck, got struck. But you know what got struck most of all? The standard blunt tipped lightning rod. Shocker. So they work as advertised. There's no reason to say, it's like building a better mousetrap. Has it been done? Yeah, I guess, sure, whatever. But the old one works just fine. Lightning protection works fine. It's still the same principle Ben Franklin used, even though he had it slightly reversed in his head. But our systems work and it's good. That's why we install it that way. That's why the code is written that way. So that you see any of these things, they don't really count as lightning protection and that system fails. Who can install lightning protection? Well, we have to pull an electrical permit. So I assume electricians can. The execution of work portion in B72 says the individuals responsible for the installation shall be competent and knowledgeable on the requirements of this standard. As you've seen, there's a whole lot to the standard. Electricians aren't generally taught that in their apprenticeship programs. They rarely run across it. We work with electricians sometimes that want to buy parts and materials and do the work, but there's always something wrong. It's always in the details. I've never seen it done 100% right once in 25 years. Who should install lightning protection? Well, I don't know. I think you should hire us to do it all the time, but you aren't contractors, you're inspectors, so you don't have any say about that. But anyway, one good thing for any lightning protection contractor worth their salt, they should be part of the industry groups, the Lightning Protection Institute. So we are listed with the Lightning Protection Institute. You can find us on their website. And this isn't me dogging on any of our competition. There's a couple other companies in Canada that are certified. And yes, our competition is Alberta Lightning Protection up in the Edmonton area, but it's a friendly competition, right? There's enough in the market for both of us. And we've been talking to him and he's going to get listed up with the Lightning Protection Institute. So you want somebody who is qualified in lightning protection, knows what they're doing, ideally has passed some of the tests that the LPI gives you, so you know that it's been done right. So, well, you can always just go to the Lightning Protection Institute's website, lightning.org. It's easy, find a contractor, whatever. But that's less for you than the electrical contractors that would be calling you to come inspect. Install our qualifications. This is again more engineering stuff that is less something for you to worry about, but you will be running into people who do the lightning protection that don't have any qualifications in it. So then that makes it all the more important to double check and make sure that they have done it correctly, because as now you have seen over the course of the past several hours, the devil is in the details and there's a lot of details. Where and when lightning protection is required in Alberta? Short answer is where required by an AHJ. There is no absolute requirement for lightning protection in Alberta, Gordon. It's when an AHJ makes it so. So Alberta Infrastructure is an authority having jurisdiction, and for their buildings, once a risk analysis says you're supposed to have it, you're supposed to have it. City of Edmonton says do a risk analysis. If the risk analysis shows you're supposed to have it, you're supposed to have it. Other than that, there is no hard requirement for a private citizen, private company, anybody building anything other than a nuclear facility or a nuclear material storage facility or generation facility. Those are the only times that the hard requirement for lightning protection would kick in. Otherwise, you're not required to. Is it a good idea for a lot of structures, healthcare facilities, high rises? Yes, it's a really good idea, but it's not required unless an authority having jurisdiction makes it so. I wish certain buildings were required to have it, hospitals, for example, but they simply are not required unless an AHJ decides to make it so. You are most welcome, good sir. And that, ladies and gents, comes to the end of my presentation. A couple of photographs of buildings that have lightning protection installed, good quality, solid, certifiable installations. Gotta love that cantilever pole that also has lightning protection. That's awfully nice there. Well done, installers, whoever that was, no idea. But lightning, as the final thought, is the most common force of nature. Most buildings are regularly threatened by it. We don't get all that many tornadoes here. We don't get hurricanes. We sure as heck don't get hurricanes up here. Last earthquake in Alberta, don't remember when that was, but lightning happens yearly. To the tune of, in the Calgary region, what was it? 25,268 strikes to the Calgary region in the past 18 years. So it happens, and it happens a lot, and it's one of the most common forces of nature that buildings are threatened by. So my job and our job as an industry is to protect against that reliably using code compliant systems that now you have been tasked with the responsibility of taking a look at every now and then. So you play, all of you folks, you lovely people coming who came to this presentation, you play a crucial role in that by making sure that the people who do this stuff do it properly. And at least now you know the questions to ask. At least now you know where to go. And I think all of you have my contact information, so you can get a hold of me if you have any other questions too. Question 6, exposed lightning conductors. Yes, that does mean referring to conductors on the outside face of a building or on a roof level, anywhere it's exposed, as in exposed to the elements, then it does need to be fastened. Email address is there. Oh, I can't give you the absolute specific answers, but they were in the presentation. And as a matter of fact, though, since that is a specific question, we may as well go back to the checklist, where the information somebody just asked for is down at the bottom. Is the insurance industry pushing for lightning protection on buildings? Good question, Daniel. The answer is they are not going to bother unless they start seeing, losses. I have seen, this was more in the States, less in Canada, but I have seen churches who could not get their insurance renewed unless they had their lightning protection inspected and brought up to code. That has happened. Yeah, so insurance companies do pay attention. And if they're seeing losses, they'll require lightning protection, hands down, yes. Definition of zone of protection. The zone of protection in CSA B72 is, I've got two different codes in my head right now, NFPA 780 and B72. 780, I think, says the area adjacent to a lightning protection system that is substantially immune to lightning strike. I didn't like that definition when I rewrote CSA B72, so I said something like the volume protected by a lightning protection system or something like that. Something along those lines. But yeah, the zone of protection is essentially the area or the volume that's protected by a given lightning protection system or an elevated air terminal. I didn't actually go through this, but just in case anybody has any interest in references, I do have them. If you're really curious and you want to do a deep dive into lightning protection, you are 100% welcome to do so. But in that case, I do believe that, good call. Yep, you are correct. The checklist says 900 millimeters. And that's because I haven't updated that checklist. 900 millimeters is the NFPA 780 number. I'll give you that one. It's 1 meter. NFPA 780 says 900 millimeters, 3 feet, right? 3 feet conductor fastening intervals. But because we are on the metric system here in Canada, the technical committee and I said, why would we put 900 millimeters? That doesn't make any sense. Let's just do 1 meter and call it a day. So we can use 1 meter in Canada. If you went south of the border, however, in Montana, they have to do 900 millimeter spacings. But 1 meter is our number for conductors. And I should send out I'll send out an amended amended checklist, and I will send out an amended list of test questions, because that definitely does need change. And that's a great catch. Thank you. I will open it to any other questions before I go have a drink and recover before I do this again tomorrow morning.
Simon, it's Larry. I'm just going to jump in for 1 minute. So I just want to review the quiz briefly. So for those of you that have the quiz, if you don't, you will be getting it via email. You do not need to submit the quiz. It's not mandatory. However, if you do want a certificate of completion for the course from EIAA, you do need to submit the quiz to me by Tuesday, October 4th. I will mark your quiz. If you got a mark of 75% or greater, I will send you a quiz. You do not need to submit the quiz in order to get continuing development, professional development or continuing education hours based on your Safety Codes Officer certification. You can simply just report it to the Safety Codes Council. It's considered to be 4 hours of training. So just to clarify that, when you email me your quiz, if you do, please indicate in your email the name that you want to appear on the certificate. So for example, if your name is Robert and you go by Bob and you prefer Bob, please indicate that in your email or whatever the case may be. Other than that, I just want to say a quick thank you to Simon for the presentation. I assume some of you probably have colleagues that will be participating tomorrow. Other than that, once again, Simon, thank you very, very much. And we will talk to you, Simon, in the morning. Once again, thank you all again for participating.
Thank you for your attention, folks. Very much appreciated. Zone of protection is the volume protected by the lightning protection system. That's what I defined it as in CSA B72. So that is the answer to that. And a couple of chat. You are most welcome, everybody. Again, thank you. We aims to please. You have my email address there. I believe it's also in some of the documentation that was sent out. I'm going to get right on changing that checklist too, because I think that's important, and that was a great catch. So conductance body needs an air terminal when it is, well, a conductance body sticks up out, by definition, it sticks out of the zone of protection, and requires an air terminal, unless it is a chunk of metal 5 millimeters or greater in thickness. A metal body of conductance. Metal bodies outside the zone of protection that are subject to a direct lightning strike. Metal bodies of inductance. Grounded metal bodies located within the zone of protection and within the calculated bonding distance of a primary conductor. These are just the definitions from CSA B72. But yes, chunk of metal 4.8 millimeters or thicker doesn't need a lightning rod, but it does need bonding to the lightning protection system, so it gets grounded properly. But if it's thinner than 4.8 millimeters, put a rod on it. All right, folks. If nobody has any other questions in the chat, I shall thank you once more for your time and attention, and I shall log off. And again, I'm available. Dobbin Lightning Protection. You can get a hold of us anytime, right? Thank you much, and best of luck to you, gentlemen and ladies.